Okay, hello everybody, and welcome to the last afternoon in this RecSys 2021. And we will devote this afternoon to the RecSys challenge. So without further ado, I can leave the stage to the other RecSys challenge chair, Sai, for the opening of this afternoon.
Yeah. Thank you. Welcome everyone, and thank you for attending. So let's get started. So we have prepared some slides to give you an overview of what exactly we have today. To get started, well, to give a bit of background, what is RecSys challenge and how it has evolved. So this has been started back in 2010, collaborating or in conjunction with RecSys challenge conference. And then this is an annual event where we typically provide problems from the companies, industry, engaging live problems. And this is also a place where the RecSys community has established where the researchers from both academic and industry solve a real life challenge problems. Of course, the goal here typically is that we have a competition setup where we have a real world application problem, and the goal is to kind of invite participants to solve these challenge problems. A short history of how it has evolved now. So it's, as I mentioned it, the RecSys conference started back in 2007, and then the first challenge happened in 2010. Then overall, we had a different set of companies sponsoring the RecSys challenge, at least the RecSys prize money for that. So we had two domains ranging from tourism, Twitter, jobs, everywhere. And this year, we have Twitter again, sponsored by Twitter. We would like to thank them for their continuous collaboration back from last year. Today, just to give an overview of what was the task for this year is that given a user set of tweets, the task is to kind of predict the different engagement types. And here, the different engagements a user can have on Twitter are like, reply, retweet, and retweet to comment. And as a main highlight, this is one of the largest data set ever the RecSys competition had. It's close to 1 billion data samples across user item interactions. And just a bit of timeline, how we have started working on this year RecSys challenge. We released the first data set back in late March, and the competition has run for close to 3 months. We ended the challenge in June 23. And then with the help of Twitter, the final leaderboard winners were announced on end of June. And then we have requested those winners to kind of write papers for us so that today we have this workshop going on where we have range of workshops filling with keynotes and the presentation from those winners. Just a given overview of numbers, what we had this year is like we have really competitive challenge with close to more than 600 teams registered or participants registered over that. And then in the final phase where the Twitter has released the test set, we had 20 teams fought for the winning positions. And overall, we had close to 100 methods submitted for that. And then today, the workshop, as I mentioned, that we have 7 papers overall, for the workshop, and we accepted 6 papers with 85% of acceptance rate. Well, so what's there today here? This is our menu here. We'll have an opening, which I'm doing right now. We'll follow this one with a keynote from Twitter, and then we have papers presented from across the first portion, second portion, and third portion. And to also highlight, we have 2 types of winning portions. One is the academic positions and the general leaderboard positions. This is the second session, and this is the third session. And we also have a panelist here who would like to also encourage discussing about fairness regarding the RecSys challenge. And we'll have a closing remarks for that. And just a bit of thanks here. These are our challenge advisors from the last year. They were very helpful when we want to set it up, our challenge for this year. And then we'd like to extend our thanks to the Twitter team. They were constantly helping us to get the data set up, leaderboard calculation, or giving all sort of support whenever we had it. And then finally, wanted to also thank the workshop chairs for setting us this platform to give an amazing program today. And then finally, we would like to thank the program committee member, where they have reviewed all the papers we had it, and then with their reviews, we have a good version of papers presenting today. With that, that's all from today, and then now we'll go to the next part.
Yeah, I think that Wendy Shi, one of the leaders of Twitter research, should be connected now. Do you hear us, Shi? Wendy, are you there?
Wendy can't hear you.
I'm actually.
Yeah, now it's better. Yeah.
Hi, Wendy. How are you?
It's quite fun to watch. I'm good.
We are really excited to hear from you about this data set that you released this year. So please start. Thank you, Wendy.
Yep. Cool. Let me get started. Hi, everybody. My name is Wendy. I lead the recommender system research team at Twitter. It literally takes a village to organize the challenge. In addition to the RecSys organizers, many people from multiple teams across Twitter contributed to the creation of the dataset, as well as running the infrastructure and the platform needed for the challenge. This includes members from my team, as well as from Meta team, machine learning, ethical, transparency, and accountability, the user modeling team, graph learning team, and the data science team. We also want to thank our functional partners, product council, and strategy and operation teams. Right. So in this presentation, much like last year, I spent 10-15 minutes to talk about why we're doing this, what do we put into the data set, our privacy considerations, what's the main difference between this year and 2020, and how do we put fairness into the final metrics. I will leave plenty of time for questions, so ask anything about the challenge or Twitter's recommender system if you're interested. So why did we organize this if it takes so much effort, as I mentioned? It shouldn't really be a surprise for anyone coming to this conference that RecSys is an important part of social networks. Or really, any product aiming at content delivery these days. It's not too far to say most social networks, news, video apps today are a big recommender system. However, there's a lack of standard benchmark available for recommender system research. And we really wanted to solve that problem because standard benchmark was one of the key factors of success of the ML development in the fields of vision and NLP. So what do we put into the dataset? In short, we provided a dataset with reader, tweet, and author side features, where we asked the competitors to try to predict various types of engagements between a user and a tweet. We collected data from 2 weeks and created a training, validation, and testing split, much like last year. One key aspect is how do we protect users' privacy, you may ask. First of all, it was to point out, like last year, all the information provided in this dataset is already public, available on Twitter. We didn't release any private information. In addition to that, we obfuscated IDs, not because we believe this will protect anything if people try to reverse it, but to increase the technical difficulty of misusing the dataset even just by a little bit. We then replaced the tweet text with bird tokens for the same reason. One important aspect is that we are not able to release real negative data, which customers are impressed with but didn't engage, because this is actually private information. Instead, we sampled pseudo-negatives from our network. Finally, the dataset is kept in sync with Twitter, so any non-public data is promptly removed from the dataset. This could be due to user setting their account to be private or deleting of the tweet. The above detail hasn't really changed from 2020. So what did we do differently this year? First, we're providing more data, a lot more data actually. We increased from 200 million to 1 billion data points this year. On top of that, we built a denser core, added a latency constraint, as well as incorporated fairness into our evaluation metrics. Last year, one of the feedbacks from competitors are that we're subsampling too much. For most of the users, we're losing a lot of information and history. To create a denser core, so our dataset is more suitable for advanced ML techniques like ML graph learning, we sampled from the densely connected nodes and customers, taking all of the edges for the 50% of our dataset. Then we uniformly sampled across the population for the rest of the 50%. We then added a 24-hour timeout limit for the test runs and constrained the inference service to use 1 CPU and 64 gigabytes of RAM. This is to create a more leveling playing field for academia teams and industry teams, at the same time to reflect the real-life constraints we have on production systems. Finally, we changed evaluation metrics by clustering authors according to different popularity and encouraged models to provide accurate prediction across all groups. As a general trend, we saw people building on top of last year's winning solution, which is what is expected. But there's also innovations due to the specific changes introduced here. This goes from speeding up inference to using NLP signals more, from using more advanced architecture like neural nets to change loss functions to adapt to the new metrics. We can't wait to see more from the incoming presentations. And that's it, really. Thanks so much for listening. And if you're interested, you can find more details in the archive paper we published recently.
Thank you.
Okay, thank you. Thank you, Wenzi. Do we have any questions from the audience? No. And I have a curiosity, because we have worked a lot together during this year and during the last year, but I've never asked you if you had the possibility to decide a dimension to analyze that the RecSys challenge should cover in future. What should be? What, in your opinion, so far has not analyzed well yet, or maybe we can do it better, or maybe you feel that it could be a thing that the RecSys challenge should face in the future?
It's a very interesting question, I guess. I would like to hear your opinion as well. But in my mind, one thing that's lacking from, well, there's one big challenge of trying to have a level playing field between academia and industry and have a public benchmark that's being consistent and always being used. So one thing we noticed in our data set is it started with 1 billion and quickly reduced to, I think, 600 million when we checked it most recently, about a month ago, or even less today. So the data set isn't static. So if we think about benchmarks in vision or NLP, those data sets are actually static. So people doing research 2 years down the line could have the same data set as the people doing research 2 years earlier. That's going to be very challenging in a recommended system because of privacy laws and all of that. Then how do we tackle that? Will be one of the things I'm thinking about. And the second thing I'm thinking about is that because we're only releasing public information in this data set, so it actually limits how useful the data it is and how real it is compared to what people use in industry. And how do you solve that problem? I do hope fields like differential privacy or kind of encryption technology can pick up pace enough so it can actually be really used in a setting where companies could release data and participants wouldn't be able to see the actual data, but still able to train the model and evaluate the model on the real production data. But that seems to be maybe still a little bit of gap there in terms of where the technology is today.
Okay, thank you a lot, Wenzi. Thank you again for your introduction to the RecSys Challenge dataset. That was really the best way to start this afternoon together. Thank you, Wenzi.
Yeah, no problem.
Now we can move to the first winner of this competition, because today we will listen to all the presentation of the winners. We will start from the academic leaderboard, the third place, with the team JKU AI Warriors in the ACM Recommended System Challenge 2021, Lightweight XG Booster Recommendation Approach, Leveraging User Features, by Alexander Krauk, David Pence, and Markus Schedel, and it is presented by Alexander Krauk. Please, Alexander.
Hello. Welcome to the first presentation of the third place academic team of the RecSys Challenge 2021. Our paper is titled Lightweight XGBoost Recommendation Approach, Leveraging User Features. My name is already said Alexander Krauk, and I work together with David Pence and Markus Schedel. So yeah, let's get started. I will first describe the challenge again a little bit, even though it was already described before. So the task of the Twitter Challenge 2021 was, as already said, that one should predict for a given tweet the engagements that a user would have for this tweet. And yeah, so in this data set, this were around 1 billion samples, and in this 1 billion samples, there were around 50 million different users. And yeah, that's quite a lot. Okay, so in this, for each of these 1 billion samples, there were 20 features provided that I will describe later, and 4 binary engagement targets to predict, like, retweet, quote, and comment. Also, the challenge took place from 22nd of March till 23rd of June. So the setting of the RecSys Challenge 2021 was that the training data was placed in 3 weeks of time, and the validation and test data was placed in the week after the training data. The next step for our pipeline was that to look at the features in the tab-separated data. So the data can be roughly split into tweet data, which consists of the tweet ID, the text tokens, the hashtags, media, links, domains, tweet type, language, and timestamp. Additionally, there is for each of the samples user data available, which consists first of the feature if the author of the tweet follows the user who is or is not the engager on the 4 targets. And also for the author and the engager, we have the user ID, the follower count, the following count, whether this user is verified, and when the account of the user was created. And we also have, of course, the 4 targets, like, comment, retweet, and quote. And if the engagement is present, then we also get a timestamp when this engagement was engaged, and this is mainly useful for validation splits, but not for training, of course. Early on in the challenge, we decided to not utilize information from hashtags, links, or domains for time restrictive reasons, and also because we wanted to keep our approach a little bit more lightweight. So the next step that we decided to take was to take all the 1 billion samples, the TSV data, and extract the so-called user index from this data. So the user index basically is for each of the for each of the roughly 50 million users in the dataset, we basically extract counts that that can be described as you can see on this slide. So, for example, for each user, we count the occurrences as author with each tweet type over the whole train set. And for each user, we count the true engagements for each engagement type as author with each tweet type over the whole train set. So this is how you need to reach this slide. To make it a little bit more clear, I have an example here. So here we can see that for the user with this ID, we have, for example, 2 occurrences when this user was an author in a tweet that was a retweet tweet type. And also we have, for example, the number of times the like engagement target was true when this user was the engager and the tweet type was retweet. This user index can later be used to extract important features. The next step was to use the TSV data to extract further features and prepare it for the classifier. For the training, we sampled 1.5 million samples from this 1 billion samples at random to keep the model more lightweight. The first step in our data loader was to adjust data types. This means, for example, the language feature was converted to a simple categorical feature. Now that we have these features prepared, we decided to extract some simple features for each of the samples. So the first type of features that we decided to extract can be described as tweet features. The first feature was the number of text tokens, which can simply be extracted from the text tokens present in the tweet data. The next feature we decided to extract was the GIF count, the photo count, and the video count, which can be extracted from the media feature. And lastly, we decided to extract the hour of day and day of week from the timestamp feature. Also, we can extract some useful features from the user data. First, we decided to calculate the ratio between the follower count of the author and the follower count of the engager. That means just the follower count of the author divided by the follower count of the engager. And also vice versa, as this showed to improve the performance. Additionally, we did the same thing for the following count. Then we also calculated the difference between the account creation time of the author and the account creation time of the engager. The next type of features that could be extracted considered information from the tweet data and the user data both. So the first feature was the difference between the timestamp when the tweet was posted and the time when the author created his account, his or her account. The same thing we did for the engager. So now that we have the simple features extracted, we took the user index, we masked some users for training at random. That means we just remove at random, say 2% of all the users in the user index. Next, we simply join the information from the user index with the samples from the that have been sampled before, and enhance basically the information for each sample. The next step was to extract one of our most important features, the target encodings, which can be extracted from the information from the user index. So target encodings are already known to be powerful for this kind of task. This could be seen in the work from Schiffer et al. Last year in the challenge. And yeah, as already said, they can be extracted from the user index information. Shortly, the target encoding feature is basically the probability of a target to be true given the category. On the left side and then the right side, we smooth it with the mean probability of all the categories. The category can be, for example, a user ID or also the user ID combined with the tweet type. But potentially there could be also other categories. The next step for our training pipeline was to add some noise to the target encodings. This was required because if the user index and the user index is extracted from the same data as is used for training the classifier, this can cause overfitting. We added a small number of Gaussian noise with 0.0 standard deviation. I will visualize in the next 2 slides why this is necessary. So on the X, so here we see the distribution of the target encodings for all users. And on the x-axis, we have the target encoding, and on the y-axis, the number of users that have this exact target encoding. And we can see here, when we look at the elements that are very high, that they are significantly higher than all the other elements. So the y-axis, this is logarithmically scaled, and this means basically that there are some target encodings that occur very, very often, but most don't occur very often, and thus the classifier can potentially learn some patterns by heart and trick the task basically. And if we add Gaussian noise, then it gets much smoother, and the model is forced to be stochastic and cannot cheat, so to say. The next step was to simply drop some of the features that did not improve the performance or seem to worsen the performance. Some of the features are the tweet metadata features. That means the hour of day and the day of the week. This is also something that surprised us, as we thought it would improve the performance, but it turned out that it actually got worse. And the reason for it is probably that the distribution of the tweets from the 3 weeks of the train data is just a little bit different to the distribution of the data in the 1 week later where the validation and test data is present. Also, we discarded the counts from the user index that has been joined before. And it's not written here, but we also removed the bird tokens, and we only kept the count of the bird tokens. So this is the data loader pipeline for the training data. And for the validation and testing data, we simply don't mask any users, and we also don't add noise as this is not required. So the next step is that we give our fully prepared samples to our classifier. For our classifier, we chose to use one one classifier for each of the 4 engagement targets. And we also took an XGB tree classifier, which is also already known to work well by previous work. This classifier is able to be trained in just 5 minutes for all 4 targets, which is quite fast. And the reason for that is on the one side that we do not use the BERT features, except for the token count, and also that we only use a sample of the 1 billion rows for training the classifier. And yeah, this improves the training time much. The next step is that we evaluate the features, that we evaluate the predictions from the classifier with the true targets. And this is done via the this is mainly done via the 2 evaluation metrics, relative cross entropy and average precision. I will not go into details for these 2 evaluation metrics, as this should be quite known. The more interesting evaluation metric was the fairness metric, which is basically a popularity-based fairness based on the number of followers of the authors in the samples. The fairness was split into quantiles of those 4 quantiles, 0.2, 0.4, 0.6, and 0.8. And yeah, based on the splits of the number of followers of the authors, the samples of the validation set were basically split. And over those 5 bins that are resulting, the relative cross entropy and average precision are averaged. And this is the final score. The reason why this is useful is not instantly intuitive, but when we look at this plot, we can see on the x-axis the number of interaction for each user, and on the y-axis the number of users that have this number of interaction. And we can see here that the users that have much more followers have also much more interactions in the data set. And users that have a lower amount of follower have a lower amount of interaction, they tend to have. And this basically results in the classifier seeing much more samples for users with many followers, and this is clearly a bias which can result in better performance for those user groups, which is bad. So now that the samples are evaluated, we received a 3rd academic place, and now let's look at our results. So this the marked result is the local result of the submitted model on the validation set, and I will now compare it to some of our other models where we have changed some hyperparameters or some features. So for example, we can see here, if we compare the submitted model with the model that does not have any Gaussian target encoding noise, then we can clearly see that for the RCE metric, the model is much worse everywhere, and this is the reason. This is the result of overfitting. Interestingly, if we just remove the target encodings, the performance is still worse, of course, than our best model, but it's not overfitting anymore, and the results are reasonable. Now we can see the result for a model that was trained, including the tweet metadata features. That means the day of the week and the time of the day. And it's not so clear that this is worse, but for most of the targets, it was worse, and so we decided to remove those features. Now to look at the to our model that was trained without of user features except for the target encodings. That means, for example, we did not use the follower account of the user. We can see that the performance is still quite okay, and this is a clear indication that the target encoding feature is one of the most important ones. Now let's look at the results of our best model over all the user bins for the fairness metric. And let's compare the first bin to the fifth bin, where we can see the biggest difference. And also we can see that our model is still biased a bit by looking basically at the results from the first and the fifth. And yeah, we can see that the results from the fifth bin are better almost everywhere. And yeah, this is the result of the bias that I explained before. Conclusions of our approach. So the main advantages of our approach are that we can train a new model in just minutes, and this is clearly an advantage. Another advantage that is maybe even more impressive is that the user index with all the user counts, it can be updated seamlessly. That means we do not need to recalculate it each time we train a new model. We just have to add new user information, and the model will improve. Also, it's robust for unseen users, as we masked out some percentages of the user index. And it doesn't require GPUs or much RAM, as the whole procedure is very lightweight. For the RAM, 16 gigabytes are enough, and it will still be quite fast. On average, it's about 10 times faster than better scoring methods on the test servers. Some remarks and ideas how our approach could be improved. So one could use an ensemble method to boost the performance, of course. Another thing that could be improved is that one could utilize the information in the link, hashtag, and domain features. And also one could use some approach to utilize the bird token information, and that is the semantic bird token information that we did not use at all. Also, one could find some approaches for improving the popularity-based fairness, as right now, as we saw, that our model is still a bit biased. Also, I want to mention that we did not use the validation set for training, as this induces over-optimistic results, of course, because the distribution of the 1 week time frame where the validation and test set are present is different from the train sets, and in a recommendation system use case, this is not very useful, because you usually want to predict for the future and not for the past. Now I'm open for Q&A. Thanks for the attention.
Thank you, Alexander, for your talk. And we already have three questions from the remote audience. So we can start with the first one. How did you decide on bad features? Did you perform feature importance?
So yes, we did feature importance and removed some of the features that had just very low feature importance. And secondly, we did multiple tests with where we used some feature groups and where we didn't use those feature groups. And when looking at the results on the train set, it was not always clear immediately. But for example, for the day of week and hour of day feature, when we looked at the validation set results for when we used them and not, then we could see that that the results were better when we didn't use them. So basically trial and error.
Okay, thank you. And the second question is, if there are many estimators in the XGB3, it might more time to train. How did you perform hyperparameter tuning?
So we basically did manual grid search. That means we just we tried out different hyperparameters by hand, and basically we did not use any advanced technique for that.
Okay, thank you. And the last one from the remote audience is a practical question. Did you use CPU for target encoding of categoricals?
Yes, we only used CPU.
Okay, I have a curiosity. You told us before that you randomly selected the subset for training. Did you respected any kind of a distribution or something, or how did you perform this kind of operation?
No, we just simply took 1.5 million samples at complete random of all the train train samples.
Okay. Thank you, Alexander. Are there any other questions from the physical audience? No. So then, thank you again, Alexander, for your great talk. And we can now move on to the general leaderboard. And we will listen to the talk titled User Engagement Modeling with Deep Learning and Language Models. The submission is from Maxim Volkovs, Felipe Perez, Cho Yu Chang, Janin Son, Sayad Norothi, Anson Wong, Powell Jankiewicz, Barum Ro. And it is presented by Choya Chang. Please, Choya.
Thanks for the moderator and also the great presentation from Alexander and Wenji. And then today my presentation is titled User Engagement Modeling with Deep Learning and Language Models. And then it's a third place winning solution from the RecSys Challenge 2021. And it's a collaboration from all the teammates from Layer 6 AI. And then next I will start my presentation to our solution to the RecSys Challenge 2021. So first, our general agenda today is that first we will introduce data partitioning, and then we will introduce the feature extraction as well as the XGBoost model use. Then we will introduce our NN classifier model use, and then finally we will introduce the multilingual language model we use for this challenge, as well as some of the interesting experiments. Then it will be the Q&A session. So first, I will give an overview of our approach. So you can see in this graph, it's an overview of our approach. So in this competition, we adopt a hybrid gradient boosting and deep learning pipeline for the final solution. We first extract extensive features that summarize information about tweet, creator, use, and the user. These features are then passed to XGBoost and neural network classifiers. In addition, for the unconstrained part of the challenge, we add a multilingual language model that's fine-tuned for tweet data to extract tweet representations. And we find that actually really helpful in the unconstrained leaderboard phase. So these representations are then passed to both XGBoost and NN as like additional feature input. And then we have a newer model, which is a supervised language model here in the unconstrained phase. And then finally, we blend all these approaches to be our leaderboard submissions. So next, I will go in detail into each of these steps, including feature extraction, the NN model, the XGBoost model, as well as the supervised language model. So first, let's take a look at our data partitioning strategy. So on this graph, it's a high-level overview of how we partition our data set. So in this challenge, we are given 3 data sets in total. In the training set, it's in blue in this graph, and then the leaderboard validation set is in green, and then leaderboard test set is in yellow. In terms of data partitioning strategy, we split 4 engagements by time and use the last 4 hours of the 3 weeks released engaged data are used for validation, and the rest is for modeling training. And then to create the training set, we use a 24-hour non-overlapping sliding window approach through the training period, as you can see in the graph. While 4 hours is a relatively small interval, it still contains over 4.8 million engagements, and we find it actually generates pretty well to the challenge leaderboard thanks to the huge data set pre-release for this challenge. So this summarizes our data partitioning strategy for this challenge. And next, I will get to the next step, which is feature extraction. So for the feature extraction, we have 4 types of feature groups. And then we have a total of 443 features in total. It can be categorized into 4 main groups, which is a tweet content features, user features, creator features, and user-creator interaction features. Then I will get into each of these feature groups in detail. So the first feature group we have is the tweet content features. What we do is we summarize content and metadata. So for example, tweet text tokens, hashtags, present media, present links, and present domains of the tweet, and encode them as one-hot categorical features. We also include the number of categorical values for each metadata field that contain multiple values. We compute target encoding for each categorical feature. Then we use the top 3 target encoding values and the statistics such as sum and mean as the features. Lastly, tweet text tokens are decoded back to text, and then we use a regular expression to generate text features, such as number of characters, number of words, number of words with leading uppercase letter, number of @handles, and average word length, etc. We actually find that these regex-based text features are actually really helpful as they can find the signal in the text. So these summarize the tweet-based, content-based features that we used in this competition. Next, I will get into the next main group of our feature group, which is the user features. User features summarize the engaging user, all the information about the user that's engaging with the tweet. We include base statistics such as follower and following count, follower to following ratio, and verified status. We also summarize past engagement for the user, such as total number of engagement for each engagement type, average creator verified status, average user creator following, and average creator following and follower counts. So to capture the type of content that user typically engages in, we also average categorical one-hot features from unique tweets in the past engagement. And this summarizes the features we use for this user feature group in this competition. Next, I will get into the next feature group, which is called the creator features. So from the name, you can see it's actually quite similar to user features, as it's just summarizing everything, all the information about the creator. So we also compute statistics on follower and following counts, verified status, and whether the user is following creator. We also compute features from creators' past engagement, both as engaging user as creator. And this summarizes the creator-based features that we used in this competition. And the last group of feature we used is called user-creator feature. It's interaction-based features. So for these features, we focus on summarizing the relationship between engaging user and creator. We compute neighborhood collaborate filtering similarity between user and creator based on the binary interaction matrix R. Similarity between rows and columns of R actually indicates the degree to which the corresponding user have similar engagement patterns for the engaged created tweets. We also summarize the joint user-creator engagement history, where we count the number of engagements of each type between the pair and various other statistics, such as time since last engagement. And this summarizes our user-creator interaction-based features that we use in this competition. So in total, we have 4 different groups of features that I just introduced, and we use a total of 443 features for this challenge. Next, I will get into the first model in our pipeline, which is the XGBoost model. So for the XGBoost classifier, it's actually pretty simple. So we basically feed the features described from above, which is 4 different feature groups, including 443 different features, and then we train our XGBoost classifier. For XGBoost, we train 4 separate binary models and 1 corresponding to each engagement type. And then during inference, we run them one by one. So this is our XGBoost classifier, basically feeding features into 4 different XGBoost models. Next, I will introduce the NN classifier we used for this challenge. So for the NN classifier, we use the same set of features, the same 443 4-feature group features as the XGBoost classifier. However, unlike XGBoost, since our input feature contains features that vary significantly in scale and distribution, we find that in practice, it's nearly always advantageous to apply pre-processing to rescale the input before we pass it to the neural network. And then for the neural network part, we examine the following popular transformation. The first one is the min-max scaling. And the second one is a standardization transformation. The third one we used is the Yale-Johnson power transform in a package. And the last one is the log1p transform that's introduced in a newer paper earlier this year. And then we examine very carefully these 4 transformations on this dataset with our feature groups. And then we consistently find that the log1p transformation works best on this dataset. And then we decide to use it for all the neural network model for this competition. And this is a graph. And then this graph is actually showing what I was just saying, that the validation set NN performance for different input transformations. We consistently find that the green bar, the log1p transformation, works best on this dataset. And then we use it for all the NN models. And then we can see that the consistent trend is the log1p transform is better than the standardization transform and better than the Yale-Johnson transform for the feature group. And then for the min-max transformation, since it's significantly worse on a smaller set, so we didn't include it in the bigger dataset test. So this is the overall trend we find for normalization in this competition. And next, I will get to our architecture and training details of our NN classifiers. Our NN architecture consists of 5 main blocks with feed-forward neural network layer and value activation in each block. The output block consists of a fully clamped layer followed by a sigmoid activation to output 4 probabilities that correspond to the 4 engagement types. Since the users can have multiple engagement with a given tweet, we optimize a binary cross entropy loss that's shown here. And then in this binary cross entropy loss, N is the number of training examples, E is one of the 4 engagement types, and then we sum over it. And the Y of IE is 1 if user engaged with a tweet, and then Y of IE is 0 if the user haven't engaged with a tweet. And then Y hat IE is the predicted engagement probability. So basically, it's a sum of binary cross entropy across 4 different types of engagement and across the sample size. And this is the training part for our NN classifier. And then for the architecture, what we are using is we train 3 different 5-layer neural network architecture. The first one is 400, 800, 500, 250, and 100. The second one is 500, 900, 600, 250, and 100. And the last one is 512, 1024, 500, 250, and 100. And the numbers represent the hidden layer size from the first to the last layer. Additionally, we have a last layer which is connected to 4 different output that's corresponding to the 4 different engagement types. And all the NN models are trained with a large batch size of 1 million engagements, learning rate of 1e-4, and we use layer-wise dropout in 0.1, 0.2, 0.3, and Adam optimizer. So that summarizes our NN architecture. And next, I'll get to our multilingual language model that we use for the unconstrained leaderboard. So for the multilingual language model, we explore the pre-trained multilingual BERT model and demonstrate that it can be used to achieve a significant accuracy boost. To adapt the model to the target tweet distribution, we first apply unsupervised fine-tuning, where we use mBERT's mask language loss training and applied it to tweet text. We incorporate this model into the classifier by taking mBERT's output CLS token and appending it into input features. And then later, after we get this, the full architecture is then trained end-to-end by propagating the gradient to update the NN and mBERT layers at the same time. So we fine-tune the multilingual BERT model with unsupervised mask language loss on 341 million unique training sets tweets for about 3 million steps, with a learning rate of 2e-5 and a batch size of 64 tweets per GPU. We see that we actually see a very significant improvement on validation perplexity from over 40 at the beginning of training to 5.72 at the end. After unsupervised fine-tuning, we connect the CLS token to the NN classifier and then do end-to-end supervised training. For the supervised training part, we use a learning rate of 5e-4 for all NN layers and 1e-5 for all mBERT layers. We actually deliberately use a larger learning rate for NN layers since they are initialized randomly and need more updates. And then the mBERT, we know that we already fine-tuned them in the previous unsupervised mask language loss style. So we use a smaller learning rate to fine-tune it supervised later. And then we find this actually works best for training the supervised language model. And then we refer to this model as SLM, which means a supervised language model. And then this is a perplexity curve that we just talked about. And then we can see that the perplexity on validation set went from over 40 at the start of fine-tuning to 5.72 towards the end. And then we can see there's an almost 8 times reduction in perplexity, demonstrate that fine-tuning is really important to adapt language model to tweet distribution, as the mBERT originally is trained on Wikipedia text, and then tweet is kind of free from text people use online. So it's quite different. And then fine-tuning is like a must-have stage if you want to use a language model. Next, I will talk about some of the interesting experiments we did for this challenge. So the first one is the leaderboard results. So before the competition deadline, Twitter released the labels for the validation data. And we later find out that fine-tuning on validation data is very effective. And we get large scans across all models and all engagement types, which is shown in the bottom half of the table in the stage after fine-tuning. From the first table, we can see that adding language model to neural network, which is referred to the SLM model, leads to a huge boost in both stages before fine-tuning and after fine-tuning across all 4 different types of engagement. And the second table is the final leaderboard results. Our approach, Layer 6 AI, achieves highly compatible performance and placing third with a total Docker inference runtime of 13 hours. We also show that our best unconstrained result where CPU and RAM restricted are removed. Here, we add the language model-based classifier supervised language model, the SLM model listed in table 1, to ensemble and observe a consistent gain across all engagements for both AP and RCE metric. And then in the after fine-tuning, you can see we have a SLM small and SLM tiny. This is an additional distillation experiments we did later, and I will just talk about it in a minute. First, we will showcase our language model analysis. So we can see in the group, in the images that languages that get largest performance boost on retweet engagement from adding the language model relative to the base and classifier that's without the language model. And then we find out in the graph that the more rare languages such as Hebrew, Dutch, Thai, and Greek get the biggest boost with up to 18% and 45% relative improvement in AP and RCE respectively. And then we guess that's because rare languages don't have sufficient engagement data for the model and to accurately capture preference for users that engage with the content. So accurately modeling tweet content can be particularly beneficial in these sparse situations for these rare languages, since this language model is pre-trained on large corpus from large text corpus such as Wikipedia, and we fine-tuned on tweet for each language. So we find that this rare language can benefit even more. And next, we showcase our distillation experiments that we did after the challenge. And then we add Amber to the NN classifier makes the model considerably more expensive to run. And then we are unable to run it on the restricted Docker environment. So to investigate whether language model can be practically used in constrained production environment, we actually experiment with distillation to reduce model size and improve runtime. So we experiment with two smaller versions of Amber architecture. We call it small, which is 2,768, 1536. And the second model is, we call it tiny. It's 1, 128, and 512. And the numbers actually correspond to the number of transformer blocks, vocabulary embedding dimension, and hidden dimension respectively. For both architecture, we first train them with distillation on Ambert. This Ambert is the unsupervised fine-tune model we trained before, and then we attach to NN classifier, and then we fine-tune end-to-end as supervised language model. The results are shown as supervised language model small, which is corresponding to the small architecture here, and then supervised language model tiny, which is corresponding to the tiny architecture listed above. We can see that even with a very compact supervised language model, which is a tiny one, we can preserve most of the supervised language model gains and still significantly improve the best and classifier. So in case you forget, just to showcase the distillation results again. So please note that in the after fine-tuning stage, we have SLM small and SLM tiny. And these are the distillation results corresponding to the previous architecture I've just introduced. And you can see even with the tiny architecture, it's a huge boost against the base and classifier. And it's not much performance drop from the original supervised language model, given that it's like a way smaller transformer model. So we can see that these distilled models, both SLM small and SLM tiny, achieve really competitive results given the size of transformer model it's using. And then it might be something that's worth considering for in production. And next, we still want to figure out if it's like useful in production. So we actually did a model inference speed test for all 5 of our models. And this figure shows the inference runtime in examples per second on the constrained Docker environment with 1 GPU and 64 gigabytes of RAM. So to score the 14 million test engagement in 24 hours on the environment, the model have to have an inference throughput of at least 160 examples per second. And then from the figures, we can see that both NN model and XGBoost models are actually very comfortably above that threshold, with NN being 120, almost 120 samples per second, and XGBoost at 434 samples per second. So XGBoost is around 3 times slower because in our model, we use 4 separate XGBoosts and ensemble them at the end, so which can only be run sequentially if we only have 1 GPU. That's why it's almost 3 times slower. So we can also see that adding Ambert significantly slows down inference, while supervised language model can only process 2.8 examples per second, and it would require actually over 57 days if in a constrained Docker environment to process a full test set. However, we see that distillation actually considerably helps runtime. In particularly, The supervised language model tiny architecture have a throughput of 133.3, which is nearly the target throughput threshold, which is at 162 examples per second for the requirement of this competition. So these results demonstrate that through distillation, we can actually leverage the representation power of language model while satisfying very strict production constraints. We believe that future engineering and experiments, both throughput and accuracy of supervised language model tiny can be further improved, which might be useful in production one day. And I think this is all for our presentation today. And in this presentation, we showcase our approach to the 2021 ACM RecSys Challenge organized by Twitter. Our pipeline consists of extensive feature extractions followed by XGBoost and neural network classifiers. In the unconstrained phase of the challenge, we further explore multilingual language models, and they show that they can lead to a very significant boost in performance. After that, we then apply distillation to compress the language model architecture and demonstrate that with sufficient engineering efforts, these models can actually be run in highly constrained production environments. And hopefully in the future, one day we can use language model, distilled language model in production with even stricter production environment requirements. And thanks everyone for coming to our talk today, and please feel free to raise any question if there's any question. Thank you.
Thank you, Choyue. We have a lot of questions for you, so we can, but we have time, so yeah, we can go through that. The first one is, there are too many users and items. Wasn't the memory of the binary rating matrix too big?
Yes, so I think there's like a huge number of users and items, but then we actually managed to fit the number of users and items in the 64 gigabyte memory with our customized Java stack, so it doesn't consume too much memory. So we are able to doing the construction of the rating matrix on the fly, on the inference environment, as well as the computation of the similarity. So I think that's very helpful because we have like a custom Java stack, which doesn't use as much as memory as, for example, if you do that in Python.
Okay, thank you. The second question is, do you transform all numerical features with log1+? And how about the features like target encoding features or conditional probabilities? The values are between 0 and 1. Is log1+ used for it as well?
That's a very good question. I think what we do is we actually transform almost all features except some of the one-hot features. So almost all of the features, like target encoding, we transform via log1p transform as well, and we find it's actually helpful.
Okay, thank you. The next question, I think that is not for you, is for us, is does anyone have a link to this paper? I can find the paper in the Hub library. And this is because the proceedings are being finalized. Almost all the camera-ready papers are there. So in a few days, you will find them in the ACM digital library. But for today, you have to follow the presentations. The next question is for you. And it says, what optimization algorithm did you use for training neural networks with large batch sizes?
Oh yeah, by the way, before I want to add something to the answer to the previous question about the log1p transform. So I think because of the time constraint of the challenge, we are not able to like do extensive experiments. So we just apply the log1p to everything except the one hot. So maybe if you do experiments, maybe it's like good to do log1p on some of the features and then do some other transformation on the other. So a mixed strategy might work even better, but due to the time constraint, so we are only able to apply one type of transformation to almost everything and then test the results. So there might be better strategies out there. So what I've seen is just like based on our experiments in this competition. Yeah, so the next, sorry, do you mind repeat the next question?
Oh, yeah. Thank you. Did you consider previous tweet contexts where the tweet are split across multiple tweets to overcome Twitter character limit?
Oh, so what we do is like, because in these competitions, there's a limit of the tweets because we need to upload a Docker environment. So there's a limit of tweets you can have. So I think we cache a summarization of them, but we didn't like build our cache based on all of the previous ones. So because that will exceed tweets limit for uploading what content you can have in the Docker environment. So what we did is we did a summarization for the previous content, but we are not able to summarize, like put everything that the user has engaged in the past in the Docker due to the Docker constraint. However, we believe that if we are able to put everything, it will get a stronger performance, but it might be even more unrealistic to use it in production. So what we did is under Twitter's range Docker constraint, so we are only able to use some summarization vectors rather than getting all the histories. Yeah.
Okay, thank you. And we noticed that we missed talking about the optimization algorithm. So the other, Eder?
So, sorry, do you mind saying that? Okay.
You continued talking about log 1 plus, but we received the other question about what optimization algorithm did you use for training neural networks with large batch sizes?
Oh, that's a really good question. So for this one, we just use the plain like gradient descent. We use the Adam algorithm for training and with large batch sizes. And we find it actually works pretty well because for our end, if you, although it's like very huge data set, but then if you batch wise it, it's like relatively small. And then when you feed it into the GPU, so we just use a plain Adam algorithm, but then I know there are a lot of like distributed and then things that can train with even larger batch size out there. But then due to the time constraint, we are not able to explore those optimization algorithms. So in this one, we just use the plain Adam algorithm for optimization.
Okay, thank you again, Choyue.
Yeah, thank you. Thank you for moderating this challenge. Thank you.
And with this presentation, we have finished our first session. We are quite early, so it's a good thing. And in the next session, we will cover all the second places for academic leaderboard and general leaderboard, and we will also the presentation of the academic leaderboard first place. And then, this session will start at 16 p.m. And then at 18, we will start again with the general leaderboard first place, so the presentation of the general winners and the 2 panels. So we will come back in a few minutes. Thank you.
And for the second session, we're going to get started now. We have now a presentation by Peter Gilbert, the academic leaderboard second place. He would talk about his approach in this paper entitled as Addressing the Cold Start Problem with Two-Branch Architecture for Fair Tweet Recommendations.
Okay, thank you. Okay, thank you very much. This is my presentation. We obtained the second place in the academic leaderboard. I am Pere Gilabert. I'm a PhD student in the University of Barcelona. And together with my professor, who is hiding here in the shadows, Santi Sagui, well, we developed a method to participate in the RecSys Challenge 2021. So this is the outline of my presentation. First, I will explain a little bit about the problem and the data that was provided for the organizers. Then I will move on to the approach that we developed. And lastly, I will present some results and show the final leaderboard. So first, let's talk about the problem. So imagine that we have two users. In this case, we have Joe Biden and Barack Obama. And Barack Obama wrote the tweet. This will be our author. And we have also a reader or a person that can interact with this author. In this case, we have Joe Biden and can interact in 4 different ways. Can interact using a like, a reply, a retweet, or a retweet with a comment or a quote in this case. So this is the data that the organizers provided to us. It was really, really huge. And yeah, there were 800 million interactions. Half of them were positive interactions, meaning that there was a real interaction, like a tweet or a reply. And the other half were negative interactions, meaning that they were sampled from the feed of the user, so the user likely saw that tweet. But yeah, they were half and half. And each sample contains 4 types of features. In this case, they were organized in this way. We have tweet features, like the hour or some information about the context. We have also, if there was media attached to it, or the language the tweet was written in, and also information or features about one author. These were like if the number of followers, if his or her account was verified, and something like that. And also the same features for the reader. And finally, the 4 targets that we need to predict were the 4 that we presented in the previous slides, that were like, reply, retweet, and retweet with a comment or quote. So all these samples were organized in 3 different data sets, as you may know. They were sampled from 3 weeks of February. The first data set was the train. And the second and third data sets were sampled from the next week, and were sampled from the last week of February and first week of March. So also, there was a lot of interactions, but there were a lot of users too. In this case, we have like 30 million users that were identified as authors or creators, and we have nearly 40 million unique readers. So it's a huge amount of users. And these 30 million unique authors wrote 360 million unique tweets in 66 different languages. Here you can see some statistics about the language. One of the news of this challenge, because we also participated in the last challenge, was the constraints that were imposed during inference. In this case, were 1 CPU with 1 core and 64 gigabytes of RAM and 24 hours maximum execution time. This led to some problems that I will comment later, because we tried like different approaches that we couldn't develop in production because of these constraints. So we also have the data organized as a very imbalanced problem, meaning that we have like 40% of interactions were like. The positive interactions were organized in this way. The 40% of them were like, but nearly, well, less than 1% was like were quote interactions. So it is a very imbalanced problem, and we tried to model this behavior in our solution. There were also 2 different metrics that the organized used to evaluate our submissions: the area recall under the curve and the relative cross entropy. The first one is a very known metric used in a lot of problems, but the other one is quite new, or I didn't use it before. It's balancing the naive cross entropy or the cross entropy using this formula that you have on the left. And also one of the news of this year was the introduction of this new concept of fairness in ranking, where authors were divided in 5 bins or 5 groups according to the number of followers. And then the metrics were computed using the average over these 4 groups, or 5 groups, sorry. So now I will talk about our approach. So imagine that we have this tweet. We decided to compute different types of features or extract different types of features. In the first place, we decided to extract interaction features that were very related to the ones that we saw at the beginning of the presentation, the ones that we can extract directly from the dataset. But we also handcrafted some of them and creating small computations on the initial features. We also extracted some relevant features from the text, the verb tokens that were provided, and we couldn't create complex models because of the restrictions, but we flagged some relevant words that we thought that could be interesting for our models. And finally, we have author and reader features that I will explain, but are mainly based on popularity or target encoding that other teams commented. But yeah, we computed all of these popularities too. So these are the interaction features that we developed for our model. You can see the number of hashtags, the number of media elements, the detailed media elements counting the number of GIFs, the number of videos, or the number of photos, something like that. And we also computed different ratios between the followers and followings of the authors and the readers. And we used also the tweet type. All of these variables, we encoded them as one-hot encoding if possible, or if they were continuous, we discretized it in some bins, and then use it one-hot encoding to input in the classifiers. So these are the text features that we created, and as I commented, we tried to develop complex models or complex sentiment analysis models, but then we couldn't fed them in inference because of the memory requirements and memory constraints. But mainly the more important ones that we developed is flagging the add token, which is the one used when you add some friend or some person into a tweet. Also, we encoded the number of unknown tokens that we saw that encoded some of the emojis and other like weird words. And also we imputed to the classifier the four tokens per tweet. The first 2 tokens of the bird, discarding the paddings and these types of tokens, and the last two tokens. So here are the popularities or the features that are related to the authors and readers. In this case, we have an author that has 5 interactions and 2 readers. We can count the popularity of an author, in this case, a like popularity of an author, as 2/5, because it receives 2 like interactions over a total amount of 5 interactions. We also used the negative samples, the negative interactions here. And in the case of the reader, if we want to compute, for example, the popularity of reader 1 in respect to the like engagement, it will be 1/4, because it gives 1 like over the 4 total samples that they appear in the data set. And we also did the same, but only filtering with per tweet type. So we computed this ratio of these popularities using only the samples of a specific tweet type. We have 3 types of tweet types. They are top level, retweet, and quote. And we used the exact same strategy that we saw previously to compute these popularities. Okay, we used also smoothing popularity, as we call it, but in fact, this is the target encoding that other authors commented. This is the formula that we used, but it uses the mean of the features you want to smooth and the number of elements that were used to compute. But in fact, if we have this user that has many interactions, we can compute this target encoding for the popularity. But in fact, we don't want to use this because if we can use this if the user has many interactions, but if they have or she have a small amount of tweets, then this formula is really biased. So we tried to develop a cold start model separately for these authors that has very few previous interactions. So at the end, our architecture, this is just a previous slide to the actual model, but just to be clear, if we have a sample to predict, we devised the sample of one of the two models. The first one is when you have enough samples to compute the popularities, and the other one is when you have very few samples, and we tried to evaluate them using the cold start model. So we tried also to solve the imbalance problem, and in order to do so, we don't use only this strategy to make predictions. We are feeding the samples to the 4 models, but we also are concatenating the outputs of the previous model to fit the more difficult one. So in this case, we decided that is easier to predict because we have more data or more positive data, and quote is very difficult to predict because it's more imbalanced. So we tried this strategy of feeding the output of the previous model to the next one to solve this problem. The model that we decided to use was the light GVM because of the fast training and low memory usage, and it can handle large data sets, also because it handles categorical features natively. And we used, as I said, 1 model per target, and used the output of the previous model to impute to the next one. And we used binary cross entropy, since it's a metric very related to the one that was used to evaluate our submissions. So this is the final architecture of our model. You can see on the top one, the active user model that we called for the active users, or users that have a lot of previous interactions. And in the bottom row, you have the cold start model. You can see that the only difference is how they were trained. The first one was trained using the author popularities, and the cold start model was only trained using text features and other features, but also reader popularities, because this is one improvement that we would like to make in the future, like also splitting for reader popularities. And you can see this was an hyperparameter, but we decided at the end to use more than 5 and less than 5 interactions to make this split. And to train validation our model, during all the challenge, we used the first 2 weeks for training and the 3rd week as validation, as almost all teams were doing. But at the end, we realized that if we changed our method, when the validation data set was released, we tried to only train our model using the 4th week and really boost our solution. So at the end, it was a competition, and we decided to move on our method to use only the 4th week to train. But the calculations or the compute of all probabilities was done using all the previous weeks. And for the cold start model, we sampled those users that had less than 5 interactions, and we used all 4 weeks. And these are the results. Well, first, some parameters that we used and that we were manually trying. We used 5,000 epochs, this is wrong, and L2 and L1 and L2 regularization, and we limited also the expansion of the trees to prevent overfitting. And we used a learning rate with exponential decay with these parameters that were also manually tuned. And this is one of the examples of our training. In fact, this is one of the 2 models, is the active users model. And you can see how the 2 curves on each plot. The first row is precision recall accuracy, and the second row is relative cross entropy. The first column of plots, the 2 lines are pretty tight, so in fact, it is learning quite better. So it's easier to predict likes than to predict quotes, for example. And the best features that we discovered, in fact, this is spoiler alert, all are popularities. But you can see how active users model, the popularity features were the best. And for cold start model were the tokens that we created using the first 2 tokens and the last 2 tokens were the best features for our model. And in fact, one curiosity is that the quote is very related to the retweet. So the second feature for the quote cold start model was the prediction of the retweet model. And these are 3 of the results we submitted at the very end. You can see on the first submission is using the week 1 and week 2 for training and the week 3 for validation. You can see the results here. And then when we introduced the training set using only the week 4, then like this boosted a lot our solutions. And the difference between submission 2 and submission 3 is with and without this dual architecture. The submission 2 used only, in fact, these were the two results we submitted at the end because they were 2 submissions allowed. So yeah, at the end, the third one was the best and was this dual architecture. And this is the final ranking of the challenge where we obtained the 5th place. So thank you very much, and if you have questions, I will gladly answer.
Well, if anybody in person has questions, please come towards the microphone. But I can see one question from the remote audience. It goes, congrats for your work. Can you give more details about how did you plot the learning curves?
The learning curves? Yeah, they are the learning curves that the LightGBM method returns. So I don't know how else I can.
Maybe a bit more details, like did you use some kind of Python libraries to plot them, or
it's basically matplotlib, and we used the dictionary that the LightGBM returns to plot the learning rate.
Okay.
Sorry, the learning rate, not the loss.
Any questions from here? I have one clarification. So you actually classified users based on the number of interaction to a cold start user or warm start.
Yeah.
How did you get this number index? So
in fact, we tried a lot of different numbers, and 5 was the best for us. So we decided to split using 5 as the number of previous interactions to distinguish these 2 types of users.
Right. And did you also try to explore, because I've seen the models mostly deployed for this challenge was from XGBoost classification boosting algorithm?
Yeah, we tried also XGBoost. And
so do you try XGBoost as well?
Yeah, we tried XGBoost, but at the end, we decided to go for LightGBM because was faster for us, and the results were pretty similar, so yeah.
Any questions? Let me check from here. Okay. I think that's it from the remote, but I have one more. Maybe I was a bit not unclear regarding how you actually pass the output of one of the models as an input to the next model.
Yeah, it's a very good question because we have a number, let's say 50 features for the first model. So then we have 51 features for the next one. So we concatenated them to all of the features we had to the next one, and that's it.
So this is as an input because this is the next tree
that
they
are trained separately. See,
okay.
Yeah.
This is separate training. Okay.
Yeah. They were trained, all 8 models were trained separately.
Okay.
So first we train light models, then we train retweet models, then we train, and so on.
If you don't have any questions, let's thank the speaker.
Thank you.
We have next as a remote presentation. It's from the general leaderboard, 2nd place. Synergize at RecSys 21. the paper titled as Twitter User Engagement Prediction with a Fast Neural Network by Mikhail.
Hello, everyone. My name is Michał Daniluk. I'm a research scientist at Synerise, and today I will present our second place solution to RecSys Twitter Challenge 2021. So first of all, I would like to thank the organizers for hosting an exciting recommenders competition. It was a big fun for us, and we really enjoyed this competition. It lasted from March 22nd through June 23rd. And the goal of the challenge was to predict user behavior when a user sees a tweet. We needed to predict whether the user liked the tweet, replied to the tweet, retweeted the tweet, or retweeted a comment. And the metrics used for the performance evaluation were relative cross entropy and the average precision for each type of engagement. Our team achieved second place on the final test leaderboard. And the data we're given to build our model has about 750 million rows in 24 columns. Each row represented one possible interaction between a specific tweet and a specific user. A third of features are about a tweet. Another third of features refer to an author or a tweet, which is marked in green as engaged user features. And another third of features are about the user who sees a tweet, here marked in blue as the engaging user. We have 4 columns that represent a target, a timestamp of like, retweet, reply, and or retweet with comment. Each tweet is represented as a set of tokenized word piece IDs from multilingual BERT model. Moreover, the data contains information about hashtags, recent media, linked domains, number of followers, engaged and engaging users, verification of both users' account, information if the engaged user follows the engaging user, and so on. The entire dataset consists of close to 1 billion data points between the 4th of February and the 4th of March. Tweets are written in 66 different languages, and the dataset consists of roughly 50% positive and 50% negative examples. The biggest difference between this year's challenge and the previous year challenge was that the organizers introduced strict latency constraints. So each model needed to be uploaded and evaluated in a separate test environment provided by the organizers, with only one CPU core, no GPU, 64 GB RAM size, and 20 GB disk space. And a time limit of 24 hours for making all predictions, which gives about 6 milliseconds per single tweet prediction. And the first 3 weeks were used for training, while the last week was randomly divided into validation and test sets. At the beginning of the challenge, the models were evaluated on the public leaderboard that used the validation dataset, and 2 weeks before the end of the competition, the validation targets were released as an extra data source for training, and a new test leaderboard was introduced. And this changed the competition settings as the validation set was sampled from the same time distribution as the final test set, while the training set was sampled from the past. It imitates the real production environment where models can be fine-tuned in real time to adapt to current trends. Another important concept in this competition was fairness, meaning that the quality of the recommendations should be equally high regardless of the popularity of the authors. And the fairness concept was included in the metrics by dividing authors into 5 groups according to the popularity on the platform and evaluating separately for each group. And the final score is the average score for each group. Finally, we didn't have access to test data, so we didn't know the user and tweet IDs in the test set. And the first step of our approach is to obtain a tweet text representation by fine-tuning a BERT model on tweets and using MD to represent text as a sketch, which is a compressed fixed size representation of the tweet meaning. In addition, we introduced the Fourier feature encoding, which allows to express continuous features in a numerically stable way without normalization. We also extract features that describe tweet content, the engagement history of engaged and engaged users, and the account status features. And the underlying model is simple, residual, feed-forward neural network that takes as input following features. Engaged user interactions summarize the history of the interactions of the engaged user by counting the number of interactions of each type of engagement which this author received. And similarly, to the engaged user features, we count the number of each type of reaction which the engaging user gives to any other user. We also count the number of interactions between an author of a tweet and engaging users. And additionally, we count the number of interactions between engaging user and the users which are similar to engaged user. Another inputs to the model are a tweet text representation, account status features such as the number of followers of each user, interaction clusters, and tweet content such as the presence of additional content such as image, video, or GIF. And in the following slides, I will describe these features in detail. And the training set was sampled from the first 3 weeks, while the validation set was sampled from the next week, the same as the hidden test set. So first, we use a training set to train our model. We apply a non-overlapping 24-hour sliding window to the training period. As a result, all training examples are divided into day-sized chunks. And engagements from a single day were used as training targets, while all the rest are used for feature extraction. We also use 90% of random validation sample for extracting features from the validation set. And the remaining 10% of validation holdout, was used for our local evaluation. The validation set targets were released 2 weeks before the end of the competition, and we were allowed to use them for training. We fine-tuned our model using these validation targets. Instead of partitioning the data per day, we randomly divided it into 10 parts. Each of them used as a training target, while the rest 9 parts were used for feature extraction. The most important features of our model are based on count and coding sum. Here I present a simple training example of interaction features that are computed. We have an author of a tweet, engaged user ID 2000, engaging user ID 3000, some hashtag ID, language ID, and tweet ID. The example is taken from a single day size chunk, and other days are used for counting the interactions. And first, we can observe that this specific engaging user ID 3000 had 2 interactions with the engaged user ID 2000, a 1 like and 1 quote. Second, we know that this engaged user received 10 likes, 2 replies, and 2 quotes in the training feature extraction part. Third, the engaging user gives 1 like and 2 quotes to any other user. In addition, we calculate the number of interactions of the engaging user with the tweets that are in the same language as the target one, and we also incorporate historical interactions between the engaging user and hashtags from the current tweet. Finally, we count the number of interactions between the engaging user and the users which are similar to the engaged user. And separately, we extract the same features from the validation feature extraction part. Additionally, we compute the reverse interactions, which we empirically found that improve the performance of our model. As a result, we compute not only interactions that engaging user gives to the author of a tweet, but also compute the number of interactions that the author of a tweet gives to engaging user. We also compute the number of interactions that engaging user received as an author of a tweet, and the number of interactions that the author of a tweet gives to any other user. Furthermore, since some tweets from the validation set appears also in test set, we calculated the number of interactions for a given tweet ID. And taken together, all these counts of interactions from training and validation sets are the input to the model. We count the number of interactions between engaging user and the users which are similar to engaged user. Similar users are detected in the following way. First, for each user U, a set of users who follow the user U is created. Then, for each user pair ended B, we compute the follower similarity score as Jacquard similarity between the follower sets FA and FB. If the similarity score falls above a threshold, which was selected experimentally, we mark the two users as similar. Clusters of similar users are pre-computed at the training stage and reused during the inference. And for submission, we have some constraints, especially based on file size. So we had to find ways to decrease the size of the files. Especially the count encoding maps we use have a large size. In this model, all the count encoding maps keys, such as user ID, tweet ID, hashtag ID, were stored in int32 type instead of string type. It saved a lot of memory during the inference and saved disk space during submission. It made some collisions between some users, but it doesn't decrease the performance of the model. And the one additional thing is that our count encoding module also uses a combination of features. We can compute a user ID with language and hashtag, and you can convert it into one hash int32 number as well. We also calculate features based on interaction clusters. We perform a community detection on directed graphs of engaged and engaging user interactions utilizing Leiden algorithm. We detect communities with default settings on 4 graphs spanned by all 4 engagement types. For each graph, we have 2 additional features. A 0-1 variable indicating if both users belong to the same partition, and the inverse of partition cardinality, which is the inverse of community size. This allows us to capture potentially complex communities of mutual interaction between users, with large communities having a lower interaction strength. And here is a quick look at some examples of additional numerical features. So there are some obvious things in the dataset, like how many followers does this user has, how many people are this user following. We also created a binary flag indicating if the accounts are verified. We also looked at a number of days since our account creation, number of hashtags, and presence of additional content such as image, video, GIF, and so on. We also add some simple categorical features which are encoded by the embedding layers. For example, the language of a tweet, a day of month, day of week, hour of a tweet. Additionally, we use one-hot encoding to encode the type of a tweet, so it gives information to the model if this tweet is quote, retweet, or top level. Okay, Fourier feature encoding, what is it? It is a technique we use to encode all numerical features. We developed this technique and used already in our previous competitions and in our production environment. Fit4All network doesn't like unnormalized numerical features, right? And Fourier feature encoding is a way to sidestep the necessity of explicit normalization of model inputs. So instead of feeding a single input feature, we transform it into a 16-dimensional vector. First, an input numeric value is divided by a few numbers representing increasing scale levels. For example, we have the input value 100. We divide it by half, by 1, by 2, by 4, by 8, by 16, and so on, resulting in 8 numbers: 200, 150, 25, 12.5, 6.25, 3.125, and 1.5625. Then, each of the 8 results is fed to sine and cosine functions. And on the right, you can see a nice visualization of this process. The numeric significance of these features is thus represented on multiple levels and in numerically stable way, as any number is brought to a small numeric interval defined by a trigonometric functions. Fourier feature encoding doesn't usually offer a significant performance gains, but it facilitates the usage of continuous features. And there is one disadvantage of this approach, is that each number is represented by 16 numbers, so the size of the model input is increased. Okay, tweet text representation. So due to the inference time limit, embedding tweets on the fly with transformer-based models such as BERT was not possible. Thus, we utilized a more time-efficient approach to representation of tweets based on pre-trained BERT vectors fed to MD. First, in order to acquire high-quality token embeddings, we fine-tune a pre-trained district-BERT multilingual model. In order to construct MD sketches, we needed to obtain per-token embeddings. We achieved this by embedding all tweets with our BERT model and computing the average per-token embedding. And what is MD? MD is a technique that was previously used by us with success in Booking.com Data Challenge and KDD Cup Challenge competition. And it is also used in our production environment. MD is a probability density estimator inspired by locality-sensitive hashing algorithm. It created sketches that are a compressed representation of variable size vector representation. So in our scenario, it compresses a variable size of tweet tokens into fixed size vector. An example of full MD algorithm run is presented in this picture. In next slides, I will go step by step through this picture. And first of all, MD operates on upstream representation vectors. In our case, these are embeddings of tweet tokens from BERT model. In this picture, we have a tweet with 3 tokens: quarantine, has, made. And each of them is represented as an embedding. And the idea is simple. We divide the item embedding space into regions and assign items to specific buckets based on similarity of the embedding vectors. In this picture, the red dots denote the embedding of a specific token. The embeddings are partitioned with a data-dependent locality-sensitive hashing algorithm. And after that, we assign each input token to a specific bucket. For example, the first and the second tokens are assigned to the 0 buckets, and the third token is assigned to the third bucket in this picture. Each partitioning is done with k hyperplanes and is repeated n independent times. The region IDs of each input tokens are stored in matrices M, which are then binarized to obtain matrices B, which form the sketches of individual tokens. And the sketches of individual tokens are aggregated with simple summation to obtain a sketch of the whole tweet. We can think about it as a histogram-like vector representation of all tokens in a tweet. It allows to compress a variable length sequence of tokens into simple 1D vector of constant size. And note that the aggregate sketches produced by MD lose information on tokens ordering. This tweet text representation is then concatenated to the input of the model. And we base our model architecture on our previous design choices, which prove appropriate for recommendations with MD, various previous challenges, and which form the backbone of our commercial system. We train a 3-layer residual fit-for neural network with 1,500 neurons in each hidden layer, with leaky relu activations and patch normalization. The input of the network consists of the following feature vectors, which are simply concatenated. First, widthwise L2 normalized sketch that represents the text of a tweet. Numeric features such as a number of historical interactions, number of followers, and so on, which are encoded with our Fourier feature encoding. And finally, categorical features such as the current day, time of a tweet, language of a tweet, that are represented by the embedding layers. The output of the network consists of 4 neurons that represents predictions of like, reply, retweet, and quote engagements for a target tweet. The model is trained by optimizing a binary prosentropy loss function for each engagement type. We train our model on single GPU card. Training one epoch on training data takes about 24 hours, and fine-tuning model using the validation dataset, which is much smaller, takes about 30 minutes per epoch. Our final model was trained for 2 epochs on the training set, and then fine-tuned for 3 epochs on the validation set. The model is very efficient and meets the strict latency constraints within the competition. A single prediction takes about 4 milliseconds on single CPU without the GPU card. Okay, in order to understand the effects of crucial parts of the training process, we conduct additional experiments. Due to the long training time, we train our models only on 90% of validation set, but use all interactions from the training set as input features. The remaining part of the validation set was used for our final evaluation. To ensure a comparable number of parameters of all models, we adjusted the hidden size to have roughly the same total number of model parameters. And the ablation results are summarized in this table. So in the interaction setting, the first row, our model takes as input only historical engagement information of target users, which we encoded with encoding count sum method. And by including tweet content features, so the second row, such as schedule representation of tweet text, presence of video, image GIF, type of tweet, we observed the average 12% increase of the average precision score and 17% increase of relative cross entropy score. And the biggest improvement is for reply reaction, which may lead to the conclusion that information about the content of the tweet, for example, information that the author is asking a question, is particularly important for reply engagement. Adding user account features such as number of followers, verification, binary flag indicating if engaging user follows the author of a tweet, improves the average precision score and RecSys scores by 0.5% and 1% respectively. In addition, we verified the impact of features based on user communities, and they increased the average precision score from 0.362 to 0.365, and the average RecSys score from 23.0 to 23.4. In the next set of experiments, so the last row in this table, we compare another representation of tweet text. We replace MD with an average of all tokens embeddings learned by our fine-tuned BERT model. Elimination of MD decreases metrics significantly by almost 3% for average precision score and 2% for RSC on average. We also verified the impact of the fairness concept by dividing the test examples into 200 quantile groups based on the popularity of the authors of a tweet. And the results are visualized in these plots. The popularity increases with the x-axis, and we can observe that there's no strong trend in the average precision score for reply, retweet, and quote reactions. However, the performance of predicting likes increases with the popularity of the author. Additionally, we evaluate our model for different tweet languages. This plot shows the visualization of the average precision score in terms of language popularity. Generally, less popular languages achieve scores similar to most popular languages, with one exception. A strong outlier is Thai language, which achieved significantly lower score in spite of being fairly popular. We hypothesize that this is due to the fact that our BERT has been initially trained on 104 languages. However, Thai was excluded from training. And finally, we see some potential improvements of our solution, which we didn't have time to try. First, we didn't fine-tune our model's hyperparameters too much. Second, we didn't take into account some time-aware features like current trending tokens or hashtags. Third, we didn't consider the time since last engagement of user, which seems to be an important feature. Finally, the more efficient inference implementation in, for example, Rust, will allow us to speed up our prediction time. And that's all from my side. You can find our implementation on GitHub. Feel free to contact me if you have any questions. Thank you very much for listening.
we have some time for some questions. But before I start, I just heard that this is one of the paper where we could see a lot of innovative stuff. A lot of models have been explored. Congrats once again for your work.
Thank you.
There are some, this is remote audience asking some questions for you. The first one is, are the count embedding sums only the sums of positive examples or all the examples in the data set?
Okay, so the count encoding sums took into account only positive examples. So we did just a positive example here.
All right, thank you. We have another question here. Did you calculate the significance level of Fourier transformation encoding feature?
Not really. As I said, from our previous experiments, the Fourier feature encoding doesn't actually improve the results very much, but it doesn't. We don't need to normalize features, so it facilitates training very much. So so it doesn't improve the results, but we don't need to normalize features.
Okay, thanks. And I have a small question on this. So maybe I missed it, but what was your pre-processing approach? Did you try to convert any of those categorical or numerical variables into some range, like how the other methods have done?
Not really. So we didn't do any pre-processing of continuous features. We use these features, the Fourier feature encoding, so we don't need to normalize any numerical features, and we use the embedding layers to embed the categorical features. So, like first of all, for example, you have a language of a tweet, so we map each language to some ID from 1 to 65, and then use the embedding layer to use these categorical features.
Okay, sounds good. Any questions from the physical audience here? Then I don't think so. Let's thank the speaker again.
Thank you very much.
Thank you. We have now the last paper of the session. This is the academic leaderboard first portion, lightweight and scalable model for tweet engagement predictions in a resource-constrained environment by Luca Carminati.
Okay, perfect. Hi everyone, I am Luca Carminati, and today I will present you the work of me and my team for the RecSys Challenge 2021. We are the trial and error team, and our paper we submitted to this workshop is titled Lightweight and Scalable Model for Tweet Engagement Predictions in a Resource-Constrained Environment. First, let's present our team. We are 8 Master of Science students from Politecnico di Milano that have been coordinated by 3 PhD students and have been supported throughout the challenge by Professor Paolo Cremonesi, who we thank very much for his support. Our final standing on the general leaderboard has been the 4th position, and we have been awarded as the best academic team. Our solution is particularly interesting from the point of view of the inference time, which is up to a quarter shorter than other top solutions in the challenge. This year's challenge has been hosted by Twitter with the goal of predicting user engagements in a dynamic environment. We had a dataset of interactions, or also called engagements, between users and tweets. Engagements are of 4 types. These 4 types are like, retweet, reply, and comment. And the overall goal of the challenge is to correctly classify each interaction with the correct probability of an engagement. The overall metrics used to score the quality of each solution are average precision and relative cross-entropy. While this year's challenge is very much similar to the one of the past year, some new characteristics have been introduced to make it more similar to a real recommendation setting. In particular, those new characteristics influenced our design of our solution. And in particular, fairness meant that the performances of our model had to be uniform across different user quantiles, depending on the number of followers they had. Moreover, the great amount of data available, up to 644 million self-interactions, meant that our solution and our pipelines had to be scalable to this amount of data. And moreover, our model had to be deployed on a resource-constrained machine offered us by the challenge organizers. And this meant that our models had to be lightweight in order to perform inference in a fast enough time. The dataset is very much similar to the one of the past year. So we had a set of interactions of users with tweets. Tweets are described by features such as their IDs or text and so on. And we also have an interaction is also described by the features of the engager user, which is the user who is interacting with the tweet, and by the creator user, who is the one who actually wrote the tweet. The challenge organizers actually gave us two splits of the dataset. The first one was available since the start of the challenge, and it was composed by 630 million interactions over the first 3 weeks of the dataset period. On the other hand, we had also a validation dataset, which was released 2 weeks before the end of the challenge. And in this case, the data were coming from the 4th week of the dataset period, which was the same as the test data used to evaluate our final solution. As a general overview of our solution, we start from the raw data, and then we pre-process them in order to reduce their size and format them in order to support our subsequent computations. Then we split those data into 2 main splits. The first one is the feature building dataset that we use to engineer our memory-based features that are then remapped onto the model trained dataset. This model trained dataset is used to train the model, validate it, and tune it. As a general overview of this presentation, we will focus on each part singularly. In particular, the first one is the data preprocessing, which consists of all the operations we apply on the complete dataset, so both the original trained dataset and the original validation dataset, to reformat the values and have them support our subsequent computations. In particular, our first basic data preprocessing operation consisted in filling the not a number values and label and code the IDs that were provided as hashes in the original dataset. Then we focused on the text preprocessing. Therefore, we detokenized the text and put it in a standard format in order to perform our computation of basic text features, which were mainly count features that counted the characters, tokens, and the words, in order to compress our representation of the content of the tweet. In particular, words were counted using a topic-like organization. So we manually defined by analyzing Google Trends some list of words which were related to a specific topic. For example, for the St. Valentine topic, we made a list of words such as love, kiss, chocolate, and St. Valentine, and we counted them in order to have a quantification of the topic of this tweet. Next, we focused on the timestamp features. We augmented those in order to enable our model to have a better similarity, to score better the similarity between different types of timestamps. And also we added an age feature of the 2 accounts involved in each interactions when the tweet was created. Next, one of the most important parts of our pipeline is the data split. We started from the intuition that temporary trends are really important for the prediction of engagement patterns. This is because there are trends that evolve over time and then fade away. Therefore, to achieve a model with the most accuracy, to achieve the most accurate possible model, data the nearest as possible to the test period were needed in order to achieve the best performances. Moreover, since many data were available more than actually needed to train the model, we needed a way to summarize those in order to enhance our performances when training the model. We achieved this by splitting the dataset into 3 parts. The first one is the feature building dataset part, which is represented in blue in the figure. This feature building dataset is the one we use to compute, to build our memory-based features without any leak of any sort on the train. On the other hand, the model training dataset is used to train the dataset after the memory-based features are mapped. And this has been split in a rather particular way because we didn't take all the data that was remaining after the feature building, but instead we focused it more on the latest week available in the dataset. So we used a rather large split from the original validation dataset, and we applied a temporal filter on the data coming from the original train. This filter filtered out the data coming from the first 2 weeks, and therefore our model has actually been trained only on data from the 4th week, so from the validation set, and the latest one of the training dataset. Then we also added a model validation dataset. This was completely extracted from the original validation in order to test the performances of our model in a setting much similar to the one of the final test of the challenge. This concludes the part about data preprocessing. For what instead concerns the memory-based features, so which are the memory-based features that we used and how did we build them, we focus on the feature building dataset to do so. And the first one we use is the most simple memory-based feature that we used is the counting features. Those counting features count the total number of co-occurrences of specific values of features across the dataset, given a specific target in that interaction. That means that we go over the feature building dataset and try to count the number of rows that present a specific specific patterns in their features. This allowed us to enrich the data of the model train with some summarized information coming from the feature building dataset. To implement this, we used a custom implemented counting procedures that took advantage of sparse matrices and ad hoc reductions in order to perform these counts in a multiprocessed fashion. As an example of counts, we can see this simple example about user ID and language ID. We can see that in order to count the number of interactions that the specific users had with tweets of specific languages, given a specific target value for the like interaction, we can go over the feature building dataset, count the row, and then store this information in a separate dataset. Then we can rejoin all this information onto the model training dataset, and this allows to have new features that can enrich the model performance. Another more complex feature we used another more complex feature we use in our memory-based fashion is the target encoding. Target encodings are a generalization of the accounts in a sense that they are a smooth probability version of them, and therefore they are a normalized view of the counts, but with some smoothing in order to increase the performances, even in cases of a low number of counts. To implement this, we took advantage of the already existing RecSys AI library, but we did a slight tweak, and we used them on different parts of the dataset independently, and then averaged the result. This allowed for a speed up in exchange of a loss of accuracy. The overall results of the application of those memory-based features on the complete dataset are shown in the slides. Those were really able to boost the performances of our model, and also to activate a remaining part of the dataset which otherwise would have been unused. Instead, for what concerns the model selection and comparison, we used our model train and validation dataset. And the first type of models that we investigated were the ones called gradient boosted trees. Those are state-of-the-art techniques and winning approaches in many competitions, also in last year's RecSys challenge. Those are backed up by open source, efficiently implemented library with a large community, and those techniques perform very well also in case of strong subsampling. We deployed them in our pipeline by using a different model with different hyperparameters for each engagement available. And the two types of gradient boosted trees that we employed were XGBoost and LightGBM. On the other hand, also neural networks are a very powerful model, able to learn complex relationship among data, but they need a large amount of data and are rather heavy to compute. We tested different configurations, and the most performant architecture we found was the one depicted in the slide. So we had an initial input normalization, then 3 fully connected layers, and then some batch normalization and dropouts in order to regularize the neural network. Differently from the gradient boosted trees, we had a different neural network for each engagement, but the architecture was shared, and so the hyperparameter tuning was common across all of these. Here you can see our final performances of each model on our model train and validation dataset. In particular, we can see that LightGBM outperforms both XGBoost and neural networks. Moreover, while doing this operation, we found out that neural networks had a very high computational cost, and therefore also the tuning was made really difficult by the difficulty in training them. Another direction we tried to enhance the performance of our model has been trying a stacking ensemble. The idea was that of joining different models in order to achieve an improvement in performance. However, the results were underwhelming in the sense that we found only a modest increase in prediction quality at a huge computational cost. Therefore, we stuck with our LightGBM models and with our 4 LightGBM models, one for each engagement type, and did not follow this route. Overall, our hyperparameter tuning procedure was based on the optimization of a log loss measure. This allowed us for a faster evaluation than implementing custom accuracy metrics. And on the other hand, this didn't mean large drops in quality of the predictions, thanks to the high correlation that we found between RCE and AP and the log loss measure we actually used. To perform hyperparameter tuning on the neural networks, we performed a random search using scikit-optimize, and then we had some phases of manual fine-tuning to find the best architectures for them. On the other hand, LightGBM and XGBoost were instead optimized using a Bayesian optimization framework. In particular, we took advantage of the Optuna library, and in particular, we used the stepwise algorithm. which was greatly important to us because it allowed to shrink the space of parameters needed to explore by transforming it from a combinatorial problem to a sequential one. Finally, we can show the results we obtained on our custom validation set. The first one we show is that actually, even if our training procedure does not involve any use of quantiles directly in the tuning and optimization of the different models, we can see that performances are rather uniform across all of engagement types. There are only two exceptions. Those are the comment class and the quantile 0, and also the retweet class and quantile 0. We try to investigate those and see whether or not there was something else to do or some tricks that were needed to balance the performance in this case. Actually, what we found out is that the comment class has only a very small support size in our validation, and therefore the results that are shown for that specific quantile cannot be considered as statistically significant. On the other hand, for the retweet case, we found out that the support size was rather large, and therefore we still have to find an answer on why there is this drop of performances only for this specific quantile. For what instead concerns the feature importances developed by our models during training, we can see that the use of target encodings are crucial to achieve the performances that we were able to achieve. This because the task at hand is really a user-based one. So there is the inherent need in the challenge to use some sort of user-based feature in order to address the probability of a user having a specific type of engagement. Note also that for what regards the comment engagement class, there was no direct usage of target encodings made directly on comments, but instead the model gave more importance to the reply ones. This because comments is a very underrepresented class in our dataset, whereas reply is more represented, therefore the features are of a higher quality, and reply and comments are really strictly correlated. Therefore, the model can also use the reply features without can use the reply features to enhance the performance on the comment engagement type. Moreover, we can see that for likes and retweet, really important features are the ones that connect the engager to the tweet with the language, number of photos, and tweet type. This means that the patterns of engagements for this dataset really depend on the specific tastes of each user, and in particular on the language and tweet type that the users prefer. On the other hand, we can also see that questions are really important for replies and comments. This is an intuitive result in a sense that if a tweet presents some questions, users are naturally pushed towards those types of interactions. So those are the final results we achieved on the general leaderboard. In particular, here we highlight the short inference time taken with respect to other top solutions. And finally, we can show some implementation details that we used during our challenge. In particular, we had a specific focus on efficiency, low computational costs, and parallelization. Therefore, we used Dask as a multiprocessing library to power up all of our data processing steps. And moreover, we adopted a specific code structure that allowed us to store all the columns separately in different files, and also all the Python code needed to process each feature was separated in different files. This allowed us to have a rather robust pipeline in a sense that also there was robustness to errors or failures in the machines. And moreover, the use of sparse matrices and approximations were able to help us in reducing the space consumption of our pipeline, and also the hardware requirements of our overall procedure. This actually concludes everything we did in this challenge. Thank you very much for your attention. We would also like to thank the challenge organizers and Twitter for giving us the opportunity of participating. Thank you very much.
Thank you. Okay, if any questions from the physical audience can just approach the microphone there. But I think I have one from the remote audience. It's a short question. Did you use any white space tokenizer?
Sorry, can you repeat?
Did you use a white space tokenizer?
No, actually, the tokens were already given in the dataset, so we did not tokenize them. Actually, the only procedure we did on text was to detokenize them using BERT, using the BERT tokens, and so invert the dictionary given even in the libraries regarding BERT. And then white space were not considered. I mean, we just splitted the words according to white spaces. We also had some other custom rules in order to maybe address some language-specific or word-specific problems that we found when counting words. But this is all.
Okay, thank you. And from my side, maybe just a curiosity question. Did you, I mean, since you're in the first place, did you also try some of other simpler models like factorization machines to explore some of the baselines?
No, given the fact that the task at hand was a classification one, we went rather directly to the models, to the most common models used in this setting. So we went to XGBoost and like GBM as our initial choice, and then we tested for neural networks. This was also confirmed by the patterns of successful solutions to the past challenge. Being the dataset rather similar, we started from what was already done, and therefore prefer to try techniques that were already proven to be successful in this context.
Yep. Don't have anything more questions here. If not, then let's thank the speaker once again. All right, that concludes our presentation for this session, but do not go anywhere. We have another session coming up with interesting panel discussing about how we go ahead with the RecSys challenge.
Yeah, we will have the last talk that is actually the winner of the general leaderboard at 6 p.m. Central European Summer Time, and then soon after we have the panel with all the winners and Twitter, and at 6:40 p.m. Yeah, we will have a panel on fairness, and we will have a lot of very important researchers there. So we will have Marta Larsson, we all know her. Then we will have Michael Ekstrand, Ludovico Boratto, and also two representatives of the Twitter research team, Luca Belli and Christian Loh. So see you at 6.
Thank you.
Them girls got nothing on your sleeves, yeah, and haters hitting this like smiley with a kiss like scrolling through your pics like got me singing this like oh mamacita, come let's get more familiar. I like your style, I like your style. Hey mamacita, come let's stay till mañana. I like your style, I like your style. When you come through you make me feel nice. Yeah, she shines so bright like the daylight. When she turn up, it stop like a red light. Yeah, yeah. my side. Says she going in, says she wanna vibe. Oh, mamacita, come let's get more familiar. I like your style, I like your style. Hey, mamacita, come let's stay till mañana. Baby, I like your style, I like your style. Girl, I wanna meet you in my next life. My girl in the dark, you're my sunlight. For you, I don't want the street life. Yeah. With you, I wanna live a good life. If we had kids, what would it be like? But tonight, let's live and enjoy life. Cause I'm on the road my whole life. Yo, me lady, yo.
Okay, here we are back, and we can now start with the last session of the RecSys Challenge workshop and also of the overall physical RecSys part. We can now move to the presentation of the winners of the general leaderboard. The NVIDIA team with the submission GPU accelerated boosted trees and deep neural networks for better recommender systems by Chris Diot, Bo Liu, Benedict Schiffer, and Gilberto Titerix. And here is with us and will present this talk, Benedict Schiffer. Thank you, Benedict.
Hi, thank you for having us, and I welcome everyone for the last session. It's Friday evening, or depending from which time zone, maybe in the morning or afternoon. And yeah, I want to present our solution. Was the first place in the overall leaderboard, and our title is GPU accelerated boosted trees and deep neural networks for better recommendation systems, as we used a combination of both techniques in a lot of different ways. So first, I want to thank all our team, like Gilberto, Bo, Chris, and our supporting team members, Jiwei, Gabriel, and Ronnie. It was like a team effort, and it's always great to work in this collaboration. So as a summary, everything up front and together, what we did in this paper on our solution is, and our learnings are like feature engineering is still important, even for deep learning models, as we heard in the previous talk as well. Same for us, feature engineering is really key. Similar to some of the previous solutions for us too, Ensemble really drives the model score and the performance. And we especially use a diverse set of models. We specifically engineered the models to be diverse, to that the Ensemble has a higher boost or performance. I will show that later. Interesting, like the single best model in RCE was XGBoost, and the single best model in terms of AP was a neural network. Some other learnings is like neural networks, as they're like more flexible, we could build like way more diverse models, and they boosted like just by themselves the ensembling really well. And finally, as we got the validation data set, we saw that stacking worked way better than like retraining or continuous learning in general. And finally, a little bit of a bonus, we accelerated our inference pipeline, and we saw like 260x speedups by using GPUs, and could reduce cost by potentially 8 to 9x, which I will talk more in detail. High level, I think for people who may miss some of the previous talks, summary of the RecSys challenge this year is Twitter provided around 1 billion tweets, 750 million tweets for training, and then there was like another 30 million tweets for validation public test data set. And it was over 4 weeks, and the goal was to predict the like, reply, retweet, or retweet with comments. A comparison to last year, like we competed last year as well in the challenge, and this was already discussed during this workshop too. I just shortly summarize it, is between the last year and this year, like the data set size was way bigger. Like instead of 150 million tweets, we had 750 million tweets for training. the B user ID has to exist in train from the validation test set. That's differently as well, which enables like more like embedding structures in neural networks. We had like 3 consecutive weeks for training plus 1 week for test, which is different. I think the biggest difference was the inference restriction in terms of we had to submit code, which could be like 20 gigabytes in file size. And we had like only a single CPU and 64 gigabytes of memory, and had to do the prediction of 1450 million tweets in 24 hours. And this drove all our design decisions, which I will talk in this presentation. We always had in mind what is like the cost of this like new feature, this new architecture in relationship to the inference time cost in relationship to the performance. And another big difference was this year too, that we got access to the validation data set, including the targets, which we could reuse for training. So as a result, we won this competition. Often there was looked at as average RCE between the 4 targets. We looked at the sum, which is then a 97 RCE if you sum up the 4 targets versus like 93 and 89. And there, we summarized it in the sum, and we scored this year again as the first place. Coming to the main point of this talk about our models and what we built. So our final solution looks a little bit complicated. It's actually pretty simple. We trained 3 different XGBoost models on the training data set and trained 3 different neural networks on the training data set and used these 6 models to break the validation data set. And then from the validation data set, we have like the input scores from the stage 1 from the training data set models, created feature from the validation data set, creating feature from the training data set, and trained 2 more XGBoost models, which we then ensemble by a simple average for our final predictions. And why this is like interesting is like often the idea is to like either retrain it completely, which is where you combine train and validation data set and train your models. Or we've seen other solution is like continuous training, where you first train on your training data set and then add additional epochs on the validation data set. We tried both of these approaches, but for us, work best is to say like we stack them, because there we have the opportunities to add new features to it from the training data set and building additional features from the validation data set, and then training new models on top of it. In addition, it helped us a lot to speed up. We didn't have to retrain and experiment with like training over the full data set. Also, we did it. By deciding this in the end, it was like we just have to use our trained models, which we built over 3 months. And in the last 2 weeks, we do the predictions and then starting to iterate over how we can build the second stage the best way. Coming first for the first stage. As I mentioned, feature engineering is key. We heard it in a lot of other talks as well. So for us, common feature engineering techniques were like converting the IDs, extracting the number of media, hashtag, links, domain in the data, extracting the first hashtag, link, domain, the length of a tweet, the number of usernames mentioned, which usernames are mentioned, special characters extracted, the first, second, third word of the tweet, timestamp features, and so on. And as you see, there's a lot of domain knowledge already inside what we can extract from a tweet. But this helped all of our model to improve the score. And one important technique, which was mentioned already to this week, so I will do it a little bit quickly, is target encoding, which specifically for boosted trees helps a lot. And the idea is that you calculate the conditional probability of a category and the target, and then apply it later. And important is like the different kind of strategies you need to use. And one which was mentioned too is smoothing, which in the end, if there's like low categorical counts, for example, the first example of the B user 1001, you have only one observation. So this target encoding would be like super overconfident or overfitted. So we smoothed it to the average global mean by applying like an average weighted average between the global mean and the specific target encoding. And then this is like more smooth together, and this prevents a lot overfitting. a second part is like how to calculate the target encoding between the different data sets in terms of, we can apply 5 folds, which we did for some models. One was leave one out. And a third strategy is we don't calculate the values itself and provide it like the raw data, which is kind of what's the sums of reply, retweet, quote, and like, and the total count of the observation for each user. And then the XGBoost on your network can figure out the combination about how to calculate the conditional probability itself. And as I mentioned in the beginning of my talk, the goal or like the advantage we saw is like building these a lot of different diverse strategies, because in the ensemble, boosting, like combining them together, boosted a lot the score. Coming to like the different models we use, they're like all having a similar structure, but by summarizing them, you see how we applied different techniques for each of the model, and adds the diversity. In the end, we compare all the models. So the first model was an XGBoost, and we used only week 2 and week 3 to calculate the feature to train our XGBoost model, and in the end, apply to week 4. The target encoding values were generated over the full data set with the leave one out strategy. And like training it with GPUs took like 2 minutes per XGBoost model. And an advantage for target encoding with XGBoost, you can see, is the target encoding extract the information from the full data set, but we don't need to train on the full data set our boosted trees. We can only use a subsample, here for example 40 million rows from week 2 and week 3, and we don't have to train it over this full 650 million rows. Because the target encoding values extract kind of the features or like the important information from the full data set, and then the tree can decide the split based on the subsample. The second XGBoost model was used over 150 million rows, but the user were filtered in a specific way that they were like at least available in week 3 and in the previous week. And we run it actually, sorry, it was 3 bags, each with 50 million rows. And here, target encoding, we had like a k-fold strategy by splitting it in 5 folds and always using 4 folds to calculate the 5th one and then iterate over it. And another strategy here was like to save storage for transferring it to the inference server, that we even calculate the probabilities in int8 instead of float 32. And this enabled us to like save space in our mapping files we had to upload. So as I mentioned, we spent a lot of time in really optimizing our inference pipeline and our models for inference as well. And as you can see on the left bottom part of the page is like what kind of categories we use. And you can see examples where we use like multi-category target encoding, where we do the target encoding on the author ID with the language and the tree type combined. And this is pretty powerful too for target encoding to have these like cross features and calculate the conditional probability. Coming to the third XGBoost model on our stage 1. And here you can see like a third complete different approach. Here we used the full week 1, week 2, and 80% of week 3 to calculate the target encoding features, and then applied only to the 20% of week 3 we split it randomly. And as I mentioned before, the target encoding value extract all the information from the training data set, and we need only 20% of week 3 to really train our models. Here you don't need to use any kind of leave one out k-fold strategy for target encoding, and this is pretty interesting as well. And this one used the idea of not calculating it explicit, more like providing the raw data, and the trees can decide it themselves, the splits. And specific here too is we did not train one XGBoost model per target. We trained one XGBoost model per subgroup based on the 5 quantiles of the so like different performance, like if you train group specific as well. Coming to the neural network part. And the neural networks, they have all like a common theme, but they are super diverse and different as well. So one part which all of them share is we joint embed the author and reader, as you can use the same ideas. Like if the certain hash is an author and it happens as a reader, it's the same user. So we learn behaviors from both input signals, when it was a reader and an author. Then we often use some kind of matrix factorization or element-wise dot product to combine different models. And we use the tokens here. And this first model, we use pre-trained BERT bilingual text tokens. So we don't use the full BERT model. We just use the embeddings for the tokens, as this was like the tokens we got by default. And then we added like additional categorical feature, continuous features, and added multiple hidden layers. And we predict all 4 targets at once. The second neural network model is a little bit more complex, or like has a little bit different structure, as you can see. Use the tokens again with a GRU layer. We add some other tweaked features to it, some fully connected layers. Then we have the reader ID with some other reader features and fully connected layers, and do the matrix factorization between the two. Then having other features, concatenate them, and do the 4 targets prediction. Here we have an auxiliary loss to guide the submodels. And we use like pre-trained BERT bilingual text token embeddings as well. And this, for example, has no author ID. And this is maybe similar to the previous talk where they found out for the cold start, they don't use author ID. This was not the intuition behind it. It was more like the author ID was already really good captured in the target encoding values. And for that reason, I decided here not to use the author ID at all. And finally, the third model is a combination with multiple matrix factorization and concatenation layer. In the end, it uses the text token as well, but this time it is initialized text token randomly from scratch, and doesn't mean pooling. This is super efficient, which is really great, and GRU did not make a big difference here. We have the author ID with auto features, the reader ID with an embedding, do the matrix factorization between reader and author, and reader and the text model, like the text output, and then concatenate all of them together through a fully connected layer, and concatenate the output with the matrix factorization output again, and some fully connected layers and the final output. So this is like kind of a really other structure again. And yeah, this enables us like the diverse set. Coming up to the scores. As I said, we see that the XGBoost 2 has the highest RCE. These are like all sums, not averages. And the neural network 2 has the highest AP. Interesting, if we ensemble the XGBoost together, we get like to a sum of 76. So we can see that the ensemble is always boosting the score. But if we ensemble the neural networks together, we come up to 79. So we can see that neural networks are more diverse, even if they each of them individually score lower, combining them as getting much higher than the XGBoost. And finally, if you combine all 6 models together, we get up to 80. This ensemble is only using the training data so far, and it runs in 18 hours. So this would be totally feasible to deploy to production, even if it's with like 6 models, probably a little bit more complex as an ensemble, but it definitely runs into the production constraint. Coming to the second stage, as 2 weeks before the competition, the validation dataset was released with the targets. And this switched the competition a little bit to like how to efficiently use the additional data. We have only 2 weeks left. You get new data, and new data is often helpful. How can we leverage it most? And as I mentioned, one idea was we just combine all data together, rerun our models, and then train over both data sets. Or the other idea is to use neural networks and just continuously training. We tried both of them a little bit, but for us, our final solution was the idea of stacking. And the advantage is that as the validation data set is smaller, we can like train our, like reuse our full trained models from the first stage, from the training data set, and just apply it to the validation data set. Second, training on the validation data set is super fast, as it's like small and it's only XGBoost. And third is we can change the XGBoost 4 and 5 models. If we continuously training, we are fixed in the same data set structure. But if we do stacking, we can add new features to it. And you can see on the left side, we use a lot of features from the training data set and use the same features from the validation data set and then stack on top of them. And we can even leverage more features. So what we did in this competition is something we call reverse target encoding. As the user ID was the same, we could calculate the conditional probability for the author ID, but merge it to the reader ID. So we know if like the reader, when he is normally an author and has like a high like probability, maybe this is a good signal how he interacts as a reader. And the other way around. So we like added here like way more feature engineering again as we come up with it. If we look then at the final score, we can see like a high boost in like our level 2 models. And we tried out all combination. Like we tried out to use only a few of the level 1 models, but the best solution was to use all 6 of the level 1 models as an input to our level 2. And here again, we can see that individual models score like 94. But if we ensemble them, we get up to 96. And the final, this was like local CV based on, I think 10 or 20% of the validation data. And the final LB was in the end 97. And we can see like here again, the ensemble was helping here a lot. And this model runs in 23 hours and I think 30 minutes. So we really maxed out our time for inference. And this is the reason like all our design decision was around making it efficient for inference. We didn't use more advanced text model features like BERT, Tiny BERT, and so on, because we needed the time to make all the other models work. And we didn't see much gain in our initial experiments. We preferred simpler models and more versus having one complex model. Coming to a small extra session in the end, there was in the beginning a lot of question about if we can use GPU accelerated inference in the beginning already, and was of course it makes sense to limit it to one CPU core as it's closer to production. But then there was the leadership for unconstrained models in terms of you can take as much time for inference as you want. But all our design decisions were already around making it as efficient as possible for the one core CPU. So we were more interested in what would happen if we have one GPU available for inference? How much could we speed up our code having like a single GPU? And our results were, even for us, really surprising. We could speed up the 23 hours and 30 minutes by 260x time, running it in 5 minutes and I think 30 seconds on a single A100 GPU. And this sounds first like, oh, this is like takes a lot of time of optimization. Actually, our team with like 4 engineers, we took like 3 days to convert all 6 stage 1 models and both 2 stage 2 models into a GPU version. And it runs end to end. Like we do all the string processing on GPU. We do all this like read to disk and Parquet and read from disk again with Parquet in GPUs, all the target encoding merging, XGBoost inference with a special library, it's QML forced inference library, the neural networks optimized. We wrote some optimized embedding layer even to make it faster. But this took us 3 days. Like it's not like, oh, we spent like a huge big team behind it in the end. It was really fast. And then the second point was, but for 64 gigabyte, you don't get a single core CPU in the Google Cloud. So for a fair comparison, we looked like, what's the smallest instance we can get with 64 gigabyte of memory, like CPU memory? And that's like an 8 core. And then we still see a 90x speed up. And then we wanted to break it down in terms of, is it like only certain models which are accelerated? And we can see over all different steps, you see like speed ups between 60x and 168x coming up in overall an average of 92x. And each of the steps were really important to accelerate. Like it would not work with only a few or like only one step. And then we compared the cost finally. Like if we run the 8 CPU instance with 64 gigabyte for 503 minutes, it costs like 36 cents per hour, which is $3. If we run the A100 GPU instance for 5.5 minutes, it's like $3.60. But if it's only 5.5 minutes, it's 34 cents. So we get like 92x speed up time. The costs for a machine per hour is like 10x speed up. So we get like 8 to 9x cost saving. This was like really interesting for us too. And we would like to see how maybe inference is switching more like to GPU, because this enables like the larger models. Then we could have used BERT and other architectures in our text model processing. Some resources in the end, like we recorded a video for our YouTube series. We have some paper, we wrote a blog post around it, and all our code is public available. And then we can switch to the Q&A.
Thank you, Benedict. You had a great talk, and even though we are running out of time, we have already 3 questions. So we'll start very quickly. The first one is, did you notice problem with overfitting when using target encoding, even with smoothing and LOO?
Sorry, what's the error? What was the issue with target encoding?
LOO.
Huh?
With the smoothing and LOO.
LOO. LOO is like leave one out. I saw like it worked. It worked actually pretty well. Like leave one out, target encoding written by cell, like a custom implementation. One concern is if you have like a category, like a column with only a few categories. For example, there are like only 3 different examples. For example, tweet type. Then you could have issues. But if as long as you apply to something like the user ID, the language with tweet type, then this works really well.
Okay, thank you. The second one is this one. There are many tweets and users. How did you create a matrix for metric factorization? I think it needs a lot of memory.
So we used the, like if it's about the embedding tables, one thing is that we used shared embeddings in terms of the author ID and the reader ID shared the embeddings. The second thing is we did a frequency threshold cut, and depending on the model, it's between like 3 or 5. In terms of it needs at least to have 3 observation or 5 observation in a data set. Otherwise, it would be a memory issue, but the other thing is it would overfit. If you see a user only once in a data set, the model can memorize exactly the data point. So this is like for overfitting and memory. Another solution is to use sparse embeddings, which saves them in gradients. We shared a blog post if you look for Merlin, medium block, and then sparse embeddings. We explained how to use it to like save more memory. And finally, there's like a plugin. Like we often run into these issues like in other production settings. And we wrote a plugin to distribute the embeddings over multiple GPUs. It's called HugeCTR. It's a custom framework, but it exports the functionality to TensorFlow. So you could distribute them over 8 GPUs if you need.
Okay.
So there's a lot of options in the end.
Thank you. Are there any questions from the physical audience? Because we have other questions online. So the next one is, which part of the inference pipeline is accelerated the most by switching to GPU?
So we accelerated all parts of the inference. Like, to be transparent, it's like batch inference, like the same task as we had to do in the competition. But we read the original TSV files with GPU and do all the text processing there, all the feature engineering there, all the model inference, all like XGBoost, neural networks. Like we did not use anywhere like pandas in my memory. Like literally we accelerated everything.
Thank you. And then the fourth one is mine. Yeah. You won twice the RecSys challenge. And you made a very efficient use of your GPUs. And I know that there are some PhD students here that are really interested in following your path. And also, some of them will play the recording of your presentation. So do you have any suggestions, thoughts, or tricks to share with them?
So sure. I think one is, really using GPU, and it's not only because I'm working at NVIDIA, makes a difference. the first time I joined I worked at the RecSys 2020 challenge. I was new at the company, and first I started with pandas, and it took like 24 hours, 36 hours just feature engineering. And I never got to any point where I could really train a model. And then I started to, actually a colleague started to explore, like Chris, QDF to run it on GPU. And it was like 2 hours or something like that, super fast. And that's when we started to switching everything to GPU for this competition. And this gave us the opportunity to run like 10 experiments per day versus 1. And this gave us like the opportunity for advice. I would really spend the time to learn these kind of tools, or to think about where can you optimize your code. Really, like, it's always like you think a little bit like, oh, I just have to execute it once. I have to do this join only once. But in the end, you will have to do it over and over again because you come up with new features. You have to reprocess the original data set, maybe they release new data set. And it's like a technical debt you build always up. And if you start in the beginning, it's a learning curve in the beginning, but you get better and better on it. And then you have these really fast pipelines. Like in these competitions for the XGBoost models, I had to do feature like exploration. I could sometimes run like 50 or 80 training runs in a day. And you just like write a for loop and you just train and train and train all the time, as it's way faster.
Okay, thank you and congratulations again, Benedict. Oh.
Well, and a second advice, including not always like efficient pipelines, efficient data structure is important too, like set of strings using like int 8 or int 16, like even like using the smallest data type which is feasible helps a lot.
Okay, thank you. Thank you again. Congratulations. And we can now move to the 2 panels. And without further ado, I want to welcome the researcher who will moderate the 2 panels. A researcher from University of Cagliari, who is very well known in the fact field, Ludovico Boratto.
Hi everyone, and thank you, Walter, for the presentation. Okay, I see that all of the participants, the first part of the panel, are already here. And as Walter was saying, this panel will be divided into 2 parts. The first part is a bit of interaction with the organizers of this challenge and with the winners, while the second part will be more an open question related to fairness, the challenges and the evaluation related to this topic. So let me introduce you to the participants to this first part of the panel, starting with Luca Belli from Twitter in San Francisco, who is one of the organizers of this challenge. Then we have Cho Yue Chang, Mikhail Daniluk, Luca Carminati, Alexander Krauk, and Benedict Schifferer. Welcome, guys, and thank you for being here. Okay, so I would start with one question from the organizers. And I wanted to ask talking about organizing a RecSys challenge, what were the challenges that you faced in structuring this task, which is more related to a use case, instead of having like one metric to optimize, which would have probably been an easier task? Luca, if you want to start maybe commenting on this.
Yes. Can you hear me okay?
Yes, perfectly.
Cool. Yeah. Well, thanks for inviting us. There's also Alex with me today from Twitter. And, you know, there is, we have thought a lot about what we should do this year for the RecSys challenge. In particular, we were trying to figure out what would be an interesting follow-up to last year's challenge, right? Because, I mean, of course, you know, bigger data set would be more interesting, but it's not just the only thing that matters, right? And so for this year, we really thought like what could make an interesting problem that would be different from last year, but still challenging for participants, yet still useful for us. And so I'm very proud of the work the team did. It was actually, when we started all of this, we thought it would be like similar or less work than last year. It turned out it was the opposite. But interestingly enough, I think there are some new things that we added this year that are very, very interesting and very important. The first one, as was already mentioned, is all this new concept of fairness for the RecSys challenge, which I'm not going to talk about right now because we are going to have a panel, as you have mentioned, in a few minutes. The other thing that I think was very, very cool is that we actually tried to bring the challenge closer to the Twitter use case. Last year it was more like, here's a challenge, you have infinite time, infinite hardware. This is not like how real life works, and that's why we added these constraints. The other thing I think I want to mention that it's very interesting is that Twitter has a lot of very close connected communities. And when we did the data sampling last year, if you just do a random sampling, you lose a lot of that. You just have random users. And so one of the challenge, and maybe Alex can talk a little bit more about it, is like how we can figure out like a smart sampling that takes into account, both the long tail of people who follow just a few people, but also like this dense core of communities that are there.
Yes, thanks, Luca. So yeah, I'm Alex. I've been working on the data pipeline and how we sample the data that we want to release to the researchers. One thing to mention is that the way we sample things is like kind of direct where we want to poke researchers into research directions. So because like one thing is that like we wanted to release a really large data set. So this was like 1 billion data points or something like that. But still 1 billion is like really, really small compared to the production setting. I think like if we were just like to take just like the next 1 billion points, it would just like take into account like maybe 30 minutes of data given current Twitter production volumes. So then for us, the question was like, how are we going to sample? So are we going to sample on time? So this is why we decided this year to go from like 1 week to 3 weeks for the training part. We can sample on tweets, or we can sample on users, or just do a random sampling like we did last year. And indeed, like we wanted to add like, as Lucas mentioned, like look at the different small communities and how like researchers can use like the interaction between users into their models. That's why we decided to include like a connected component into the sample, and we had to try to find parts where we get some users who are consistently present over the 3 weeks and who are interacting with at least X amount of users. So yeah, the goal was like to find like this connected component so that like this could enable some research about like graph machine learning, or just like looking at all the history between these three users. And the challenging part was like, yeah, how do we sample that, and like how to try to keep this more graph over like the 3 weeks.
Okay, thank you. Sorry, Alexander, I forgot to introduce you at the beginning of the panel. Also, Alexander is working at Twitter and was one of the organizers of this challenge. So thank you for these insights. Then I would move to the actual winners, and we have some of them here connected via Zoom, and one of them is here in presence. And what I would like to have is a bit of a quick round of feedback in terms of what was the participation to this challenge like. Maybe some positive aspects, why not some challenges and some aspects that you would like to see improved in the future RecSys challenges. So maybe I can call you one by one so that it's easier to start. Maybe you can start with Cho Yue.
Yeah, hi, can you hear me okay?
Yes, perfectly, thank you.
Yeah, thank you, and thank you for moderating this great workshop. And then also, I think thanks Twitter and organizers for organizing this amazing challenge and the released industry-level data set of this size for benchmarking different performance of recommendation system algorithm. So as our group is also working on recommendation system research, we also see that there's exists a huge gap between academic research in recommendation system, which mostly use IMDb or Movie Lens or like Amazon dataset as a standard, which is fairly small. And then also the industry problem, since we are also solving industry use cases, which is normally billions of data size. And then we also, as a both team working in applied and research work, we also see this huge gap. And we would like to thank this challenge for releasing such a huge industry level data set for helping pushing both the limitations of RecSys applications as well as research. And then when we have a roundtable among ourselves to see what question we want to ask about Twitter a few days ago, we actually have one question that our teammates raised, and we all agree that's like a valuable question, is that, so we know that in this challenge, we have a training set, a validation set, and a test set. And then when considering from, for example, real life deployment perspective, the validation set and the test set, they actually happen at the same time scale. So actually the validation test set, both of the data and the labels, they actually won't be available while you performing inference on the test set in real life deployment scenario, as they actually happen in the same time scale. And then our team is like wondering, the question we have when we have the roundtable is that like, what's the motivation behind releasing the validation set data as well as labels, since it might actually have the risk of potential leaking, since it is from the same period with the real test set data. So I think that's the question from our team. Thank you.
Okay, thank you. Luca, Alexander, do you have any insight on the question from Choyu?
Yeah, no, it's a great point. I'd say, you know, these are very complicated pipelines that we try to set up for this. And this, we thought it was a solution that balanced sort of internal feasibility with the challenge sort of aspect. But I do agree with you that there might be data leaks for this in this case, and the real world scenario will be a little different. Although I see this challenge almost as an abstraction and a simplification of what would actually happen in the real world. So, you know, we thought that would be sort of like an okay simplification for in that context.
I wonder about like asking you, like Joey, like whether using this like training, like this validation set, like helps your performance, or something that like you just like, hey, more data, so like we'll just train with it and see what happens. Did you see any benefit of using this?
Yeah, so we actually found out pretty late. So we see like actually, oh, can you hear me? So before we are training in the like very large data set, and we have like trained models, and then later what we find that might be leaking is like when we train only on the release set, it actually outperformed the result that we trained on the entire huge set, which is maybe hundreds of times bigger than the release set. So I think maybe the reason is it's from the same time period, so they share more things in similar. But then, yeah, training on that actually gives like a very huge boost. So we have a second stage which kind of trains on that smaller set. Yes.
In general, I think that's a good lesson. Like in production, like you maybe like are training on like a large batch, and this is like early models. And then later, as like your pipelines improve, then you are trying to interpret like more recent data. I think that's something that we did recently at Twitter, where like we just like continuously training. So that makes sense that like we get more better performances like that.
Oh, so it's like you are trying to simulate a setting of like online learning, continual learning. So when you have new batch data coming in, you are trying to learn that, which is from a newer time period, I guess. So that's kind of the motivation, you mean?
I don't know if it was like conscious to include that into the challenge, but like, yeah, that's closer to what's happening in production.
Oh, okay. Yeah, that sounds good. I think that's my question. And thanks again for releasing this like huge data set for benchmarking. And hopefully, I'm not sure if it can be used for academia purpose. And then because we find that actually the language model we train is like very, very interesting. It finds like, because on Twitter, people don't really spell words like properly, like they have maybe repeated characters and then, which is like never seen in Wikipedia. And then, yeah, just thanks for this huge data set and then find a lot of interesting patterns in both the language and the thing. Yeah, and thanks for answering the question as well.
Okay, thank you. I would kindly ask the following speakers, the following participants, if we can have quick interactions, otherwise we run out of time. So, Mikhail, what about you? Any feedback?
Well, what I like most is the strict latency constraints in the model evaluation phase. I think it was a very good idea that each model needed to be submitted, and evaluated in a separate test environment. And in addition, we didn't have access to the user and tweet IDs, so we needed to keep features for all users in the memory. However, I agree with the previous speaker. I have really mixed feelings about releasing the validation dataset along with targets. On the one hand, I think it was good because it imitates the real production environment where models can be fine-tuned in real time to adapt to current trends. And we had access to recent interaction and we can use them to make predictions. But on the other hand, we had access to the future data and you can use them for training and making a prediction to the past tweet, right? So I think the solution to this problem might be that we should have access to the data streaming in time order, making the prediction and use recent past interaction as input features to the model. And definitely we should not be able to use future interactions to make a past prediction. And also agree with the previous speaker, what is, training only on much smaller validation set brings better results on our local evaluation than training only on huge training set. And yeah, again, thanks for organizing such an amazing competition. Yeah, thanks a lot.
Okay. Thank you. We have Luca here in person. Do you want to give your feedback?
Well, as a student participating to the RecSys challenge, I think it has been a very great opportunity that you gave to us to work in such a high scalable big data environment. It is not something you see in every university course, so it has been really challenging. Also, a different set of tools that you would never get to use in a university scenario. However, I think that such a huge amount of data can also scare many people out of the competition, because to manipulate all these huge amount of data, what you need is also the computational resources to participate to the challenge, just to analyze them. On our side, we had the luck to have a research team able to support us in doing this, but maybe this is not the case for most of the universities around the world. So our consideration was that what are your opinions on this? And maybe a possible proposal could be that of, I don't know, evaluating solutions also for their complexity. when scoring them, and not only as a, let's say, general constraint to the inference time to use. These were like our main thoughts when discussing about what to ask in this panel.
I agree that this was a bit challenging. Like even like last year when the data was much smaller, there were like the lockdowns started to happen, and people were staying at home with like a low DSL collections. This was like challenging, and like we thought about like how to provide either like a smaller data set, like a different challenge, or to provide like infra where the data would be hosted, saying they create something like that. But I think like why it didn't happen is that because we didn't have like the right infrastructure. It would take like too much effort to actually like build this infra to make user like train on our premises.
Okay, thank you. I would move to Alexander. Any feedback from your team?
Hi. Yeah, I also want to thank Twitter for providing this amazing data set. It's really such a large scale set available. I basically also noticed the same things that were mentioned already. Basically, first that the validation set helped basically get over-optimistic results, and yeah, this is not quite optimal in my opinion. I would also suggest something where we only always have the past tweets as training data. Maybe as we already have this more or less complicated Docker environment, it would be possible to have some sort of backend where we always make predictions and then get the new data and sort of have the model train inside the Docker instance, but I'm not sure how hard it is to implement it for some challenge. And yeah, also the other consideration that the data set is just very large. Yeah, it's really a bit scary in the beginning, in particular if there are not so many resources available. So maybe if it would be possible to just sample a dense subgraph of this huge Twitter graph, it would be better. I'm not sure how hard it is to do it, but it might help to just take tweets from a certain subgraph.
Okay, thank you, Alexander. Then we move to the last and winning team. Benedict, any feedback from you?
Yes, I think I can add like the same thoughts. So definitely thank you for organizing this challenge, particularly with the inference constraint. This was probably not easy to set up. I feel positive about the large data set. Maybe as we hear that there's like challenging on the other side, if there's like maybe like kind of two competition, how was this time unconstrained and constrained leaderboard, maybe there's like or academic and industry prizes where there, maybe there's like the large data set to compete, and then there's like a smaller data set enabling like other people to participate which don't want to work on the full scale. This is maybe an opportunity. And yeah, another option about the validation data set and test data set. I don't know if it's possible to make like 2 weeks, like the train data set, and then you have the validation from 1 week, and the test is then from another week on consecutive data. But yeah, in general, I really enjoyed working on this competition. And it's even like on this large data set, it's fun to see how things scales and to make it like, it's really getting to the scale, which is like really interesting to like, what can you compute, how you have to write efficient code. It's not like you can just throw resources on it. No, you have to write efficient way the resources that it really works in the end.
Okay, thank you. One final quick comment before we close this first part of the panel. Benedict, when your prize was announced, you decided to donate this your prize to the Women in RecSys team. What made you decide to do this? And
yes. We are like in the position that we competed from our company NVIDIA as well. And there we decided that we want to give back to the community. Last year we donated the prize money to Black in an Eye last year for helping the diversifying, to add more diversity to our field, to accelerate this. We have more diversity in our field. And this year we wanted to, we donated it to Women in RecSys for the same reason that it's going back to the community, the RecSys community, and there's enabling the field to be more diverse, adding more researchers in it, and they can use it for in the best way to achieve this goal.
Fantastic. Okay. Thanks a lot. I would close this first part of the panel. So let's thank our participants and thank you. Okay, and we move right away to the second. Okay, yes, and we move right away to the second part of the channel, which, as I said, will be a broader discussion on fairness challenges and evaluation. Remotely, we have the team from Twitter, so we have Christian Lum, Luca Belli, and Alexander Lung Yut Fong. And here in person, we have one of the general chairs of this year's RecSys, Martha Larsson from Radboud University. And also online, we have Michael Alexander from Boise State University. Welcome to all of you. So, hi. So I would start with Martha, maybe as one of the general chairs when you were approached for this RecSys challenge. What made you decide to tackle fairness as a challenge in this particular conference?
Thank you. So let's see, what made you decide? I think I'd like to reformulate the question into what made you reach out to the RecSys challenge team and encourage the integration of fairness into this year's challenge. That's more true to how things evolved. Well, I think that it's the fact that we have kind of a gap that we're facing in our community, and that's the gap from how to move to the problems that we are used to working on and which are quickly becoming, yesterday's problems. How do we move from there to tomorrow's problems into, new terrain that we might not be familiar with? And sometimes, when you have an idea, it seems impossible. So you have to get together a group of people and you have to talk about it. You have to do a lot of talking. You have to do consideration. You have to do design of a task. And so I guess I was, really interested in suggesting this because I had this sort of understanding from my experience in benchmarking that if we had the will, we could jump over this gap from doing things that were in our comfort zone to doing things that we'll need to be doing tomorrow.
Okay, thank you. And maybe I would go back to the organizers and ask Christian and Luca, what was more challenging in the preparation of this challenge?
Well, where do I start? I mean, so, as I mentioned earlier, we wanted to offer a challenge that would be interesting to the community, but also not entirely trivial. And so we had to make a lot of choices. Mostly we had to make a lot of simplifications for what would go and what would not go in the challenge. So for example, as you might know by now, the problem was giving a tweet and the reader, can you say what's the probability of the reader engaging with the tweet? So that seems to suggest that there is this one model that outputs this probability, this number, and we can control that. You know, in reality, it's not as easy. In reality, we have a lot of different models that interact together and will produce a final ranking. And so even internally, when we go and work with different teams, sometimes we think that, you know, there is this one product that might be just one model. And then we talk with the internal team and we realize that that piece that we thought it was one single piece, in reality is, you know, it's a combination of multiple pieces. And that's really, all these pieces interact in a way that sometimes it's surprising, right? And so, of course, here we wanted to give something that was sort of digestible and like that you could work with, and so that's why we decided to only have sort of one model. But there is always this question of, like, for example, talking about fairness, there is the system level versus sort of depends on the granularity. Like, what is the impact of all the models that interact together? And you know, even the choice of the metric is not trivial. Maybe Christian can talk a little bit more about that. But how everything in reality is much more complicated. And like a lot of the literature is very US centric and very binary. We're always looking at two groups, balancing across these two groups. In reality, there is way more than that, and I don't know. I think Christian is, can tell us more about that.
Right. Thanks, Luca. Right. So Luca was saying how they're often in the academic literature, when we talk about fairness, we're kind of reduced to looking at it in terms of either a small number of groups, or in some cases, especially when we're talking about theory, two groups, so a privileged or an underprivileged group. In practice, like Luca was saying, we tend to have a lot more groups, especially when we start talking about intersections of groups. Oftentimes in the academic literature, you'll see the groups defined by sensitive attributes, say race, gender, things like that. In practice, we often do not have that data at all to even form those groups, which adds another level of complexity. For this particular challenge, the sort of sensitive groups with respect to which fairness was defined was, follower count. And so that wasn't an issue in this case, but certainly it's a consideration. How do you define groups in a way that are meaningful to bring about fairness in some way that, has some meat to it, right? That actually does something in the real world when you lack that data. Sort of speaking more to what Luca was saying about designing the metric, I think this really comes into play when we start talking about having many groups. So for example, say we wanted to design a metric that looked at fairness, not just across, say, the 5 quintiles, like was done in this case, but say across all of the countries or all of the languages that are spoken, something like that, right? Then you end up with groups maybe on the order of hundreds. And so in a lot of cases, I think when you look through how people have handled this in the past, they'll define some metric that is minimized when all of the groups have the same performance. But in practice, it's not that there's one metric that we're trying to optimize. Humans are trying to balance trade-offs among a whole lot of different metrics. So it's not a matter of just reaching 0 with this one metric. It's a matter of actually measuring the distance from 0 in a way that's meaningful. And so, there are many different functions that will achieve 0 when all of the numbers are exactly the same. Which one of those is the right one? And which one of those, conveys the information that we actually need. In practice, I think it's probably not just one metric. It's probably not something like just the mean absolute deviation across all of the different groups. It's probably something that's multidimensional, right? So we would probably want something like that. We might also want something that tells us how many groups we don't have much data for. There's all sorts of things we'd want to consider. So it's not reducing it to one dimension, it's maybe reducing it to 3 or 4, but at the same time balancing this trade-off that humans are going to have to be using these metrics to make decisions. And so, taking it down from, we have 300 different, say, model performance metrics across groups down to one dimension. Maybe that's too few. Maybe we can come up with 5 that's meaningful. There's sort of this trade-off again that we're trying to balance, defining metrics that humans can use to make decisions while not losing all of the relevant features or the relevant facets of the problem. And finally, I'd say with fairness, there's a lot of nuance to all of this, right? And so I think one of the challenges with even designing metrics in this case is conveying and keeping in mind that this isn't the whole story. You always still are going to need people to be understanding the impacts of the algorithm, understanding who's being impacted in different ways, because there are things that any sort of lower dimensional representation is going to miss.
Okay, thank you. Now I would like broaden up a bit the scope, since this is a panel that is related to fairness challenge. I will start with a question by the audience, both here and online. If you have questions to ask them, feel free. We have a great team of panelists, so please interact with us. And maybe I will start with Michael. And as computer scientists and as RecSys researchers, of course, we tackle fairness from a technological point of view, but clearly these problems are tied also to other disciplines, I don't know, from legal to ethics. So I would like to ask you, how important is it to have some grounding, some foundation when approaching fairness problems in our area?
Okay. It depends a little bit on what we mean by grounding. In terms of formal study, it's probably helpful. I don't have any particular formal training in most of the relevant intersecting disciplines. What is crucial, though, is to read and listen and learn, and to read interdisciplinarily, because we can't solve the problems just from a computational lens. And if we try, we're almost certainly going to come up with solutions that aren't going to address the real problems that are concerning people, that are going to have unintended and quite likely harmful follow-on effects. So it's very important to do the homework, to read broadly across disciplines, and I really value those who've done the work of doing some of that translation and presenting legal theory, presenting philosophy, presenting sociological work in a way that is approachable for computer scientists. If people want a place to start, one of the good ones is Solon Barocas and Andrew Selp's article, Big Data's Disparate Impact, which is a really good starting point for just understanding how what we think about in machine learning and how what gets thought about in at least US legal theory intersect, to start to learn the terminology so that you can do the reading. But it's crucial to at least be reading and studying and talking with people working on it across disciplines, because if we run off and try to do it just with computer scientist hats on, we're going to produce a lot of computational results, but we're probably not going to have the positive social impact that we're trying to achieve.
I agree. Okay, thank you, Michael. Is there any other question? I see that online there are no questions coming. Is there anybody here from the audience who has some questions or comment on this topic, or a question for our panelists? We have we have Manel here on stage who is approaching the microphone and there's a question. Please.
Hello. Yeah, I will profit from this opportunity. My question can be for everyone, and maybe starting with Luca. So before publishing the data, how did you think about privacy? What did you add to the data? Is there any manipulation you made? I I was listening to sampling or maybe randomly choosing users. Is there anything else?
Yeah, thanks for the question. We did indeed thought a lot about privacy and how do we respect privacy of our users, yet at the same time provide a data set that's useful for research and for this challenge. And so the first thing I want to say is that all the data that has been published as part of the RecSys challenge, it's already public, in the sense that, as you might know, Twitter, if you're a public user, Twitter data is public. So you can literally find the tweets on the app, on the Bird app, or you can have them through the API. In fact, the data we share through the challenge is actually a strict subset of the data you could get through the API. For example, we decided not to include any of the profile description because we thought that could lead to some nasty sort of like side effects. And so I think that sort of like reframes the question a bit, because again, it's not that we have shared some data that was originally private, and so we had to make sure that we would not leak anything. We just repackaged something that was already public, and as I said, we removed something even. So I'll say like two quick things to make things a little more like harder to re-identify. We're also very aware that re-identification with public data is trivial. So yes, we scramble user ID of like users and tweets and whatnot, but again, we are aware that this is not something that is sufficient. Although there are a couple of things we did. One, we removed the tweet texts and used Bird tokens again to make things not as straightforward. And the other part, which I think it's interesting, is the negative. So the data set has positive and negative samples. So the negative samples would be in real life would be a tweet that a user saw but decided not to interact with. Although only when you publish a tweet, you are the only person who knows who. You don't even know who. You only know how many times your tweet was seen. And so releasing negative samples would have been a privacy leak, right? And so what we did, we just released pseudo-negative samples, which means among all the tweets that the people you follow, that were produced among the people you follow, we picked the ones that the reader did not interact with. And so we call this set the pseudo-negative. Why pseudo? Because we know for a fact the reader did not interact with those, but we do not know for a fact if the reader even saw those. And so I think that is the, some of the most important thing we did for this problem.
Okay.
Thank you.
Thank you. Okay, since I think we are heading towards the end of this channel, I would close this panel, thanking again all our panelists and attendants. Please give them a round of applause. Thank you guys for being here. And I would call Walter for the formal closing of this RecSys 21 challenge.
Okay, it's always very difficult to speak after these giants, and I would like to focus on the thanks. We have talked with the other RecSys 2021 challenge chairs, and we have a list of people to thank. First of all, obviously, all the participants, because they were the backbone of this RecSys challenge, but also we want to thank Twitter for all the effort, all the work that the different teams have done. And then we want to thank Ludovico for moderating these panels and all the panelists that we had with us. And finally, and most importantly, we would like to thank our general chairs, because in this hybrid conference, during this year, we had a lot of different problems that came up day by day, and they were always available to solve the problem with us. So thank you, and thank you for all the help. And see you the next year.
Yeah, thank you. We appreciate your all the work that you put into organizing the challenge, and that you took this leap to fairness as an idea, to really realizing that. And yeah, thank you very much, challenge organizers. And of course, thank you also for being the last session today here at the Burst. Yet we have more RecSys to come tomorrow, so we're going to leave now this beautiful building, which has been our home for the past week, and we're going to see everybody tomorrow online for the last set of virtual workshops, and then you can also watch the RecSys videos that you might have missed on the hub and still ask questions in the 2 coming months. So thank you everybody for being here, and where are the other GCs? There they are. Oh, taking pictures, okay. Yeah, okay, so see you tomorrow. See you online.